Hey, welcome to our Nape Wave of Discovery. I'm so happy you're here with me today. There's something truly magical about taking a moment to step away from the rush of everyday life and diving into the wonders that surround us. Whether you're curled up with a warm cup of tea, taking a break from a busy day, or simply looking for a gentle escape into learning, you've found the perfect place. This is our sanctuary where curiosity meets tranquility, where complex ideas unfold like petals of a flower, slowly and beautifully. I want you to feel completely at ease as we embark on this journey together. Think of me as your friendly guide, someone who's genuinely excited to share these incredible discoveries with you. We're going to take our time, breathe deeply, and let each fascinating detail wash over us like gentle waves on a peaceful shore. Today we are diving into the fascinating world of how volcanoes cool the planet. Now, I know what you might be thinking: volcanoes and cooling don't exactly seem to go together, do they? When we picture volcanoes, we imagine roaring fires, molten rivers of lava, and intense heat that can melt rock itself. But here's where nature reveals one of her most beautiful paradoxes, one of those delightful contradictions that makes our planet so endlessly intriguing. As we settle in together, let your mind open to possibilities you might never have considered. Picture yourself as an explorer of ideas, ready to discover how these mighty mountains of fire actually serve as Earth's own air conditioning system, cooling our entire planet in ways both subtle and profound. Imagine standing at the edge of a great volcanic crater, feeling the warmth rising from deep within the Earth, watching as wisps of steam curl upward into the sky like ghostly fingers reaching towards the heavens. The ground beneath your feet thrums with ancient power, and the air carries the distinct sulphurous scent that speaks of deep earth processes most of us never witness. This is where our story begins, not in a laboratory or a classroom, but right here at the raw, beating heart of our planet's geological soul. Volcanoes have been humanity's companions throughout our entire existence on this earth. Our ancestors watched in awe and terror as these mountains breathed fire, shaking the ground and painting the sky in shades of orange and red. They wove stories around them, creating myths and legends that tried to explain these incredible displays of natural power. The ancient Greeks believed that Vulcan, the god of fire, had his forge deep beneath Mount Etna. Hawaiian cultures spoke of Pele, the passionate goddess of volcanoes, whose fiery temperament shaped the islands themselves. But what our ancestors couldn't have known, what we've only discovered through centuries of patient scientific observation, is that these apparent agents of destruction are actually among our planet's most important climate regulators. Let me paint you a picture of what happens when a volcano awakens from its slumber. Deep beneath the surface, perhaps 20 or 30 miles down, temperatures reach levels that would melt steel in seconds. Here, rock itself becomes liquid, flowing like honey, warmed by summer sun. This molten rock, which we call magma when it's underground, carries within it not just the heat of Earth's interior, but also dissolved gases, water vapor, carbon dioxide, and most importantly for our story today, sulfur compounds that will play a starring role in cooling our planet. As pressure builds and the magma finds weakness in the Earth's crust, it begins its journeys upward. Picture this slow, inexorable rise, like a bubble of air rising through thick syrup, but on a scale so massive it defies easy comprehension. The magma pushes through cracks, melts through solid rock, and gradually makes its way toward the surface. This journey might take days, weeks, or even months. All the while, the gases dissolved within the magma are preparing for their grand entrance onto the world stage. When the eruption finally comes, it's like the Earth taking a deep explosive breath. The magma, now called lava as it reaches the surface, pours forth in spectacular displays that can be seen for hundreds of miles. Rivers of molten rock flow down mountainsides, creating new land as they cool and solidify. But here's where the story takes its most fascinating turn. While the lava flows grab our attention with their obvious drama, the real climate action is happening in a realm we can barely see. Mixed in with all that visible fire and fury are countless billions of tiny particles and gas molecules being launched high into the atmosphere. These aren't the thick black clouds of smoke you might see from a house fire or a factory. No, these are something far more subtle and, as we'll discover, far more powerful in their ability to influence our planet's climate. When a major volcanic eruption occurs, it's like nature opening a pressurized valve that's been building up for possibly hundreds or thousands of years. The sulfur compounds that have been dissolved in the magma suddenly find themselves free, combining with water vapor and oxygen in our atmosphere to create something remarkable. Tiny droplets of sulfuric acid suspended high above our heads. Now, before you worry about acid rain falling on your garden, let me assure you that what we're talking about happens so high up in the atmosphere, in a layer called the stratosphere, that these particles have plenty of time to spread around the entire globe before they ever make their way back down to Earth. Think of these microscopic droplets as nature's own Venetian blinds spread across the entire sky. They're so small you could fit millions of them on the head of a pin, yet when there are enough of them floating around our planet, they create a subtle but incredibly effective filter for incoming sunlight. It's like having a pair of very light sunglasses for the entire Earth. Not dark enough to block out the sun completely, but just enough to reduce the amount of solar energy that reaches our surface. This is where volcanism reveals its beautiful paradox. These mountains that seem to embody heat and fire actually serve as Earth's thermostat, providing a natural cooling mechanism that has helped regulate our planet's temperature for millions upon millions of years. When the Earth gets too warm, increased volcanic activity can inject more of these cooling particles into the atmosphere. When it gets too cool, reduced volcanic activity allows more solar energy to reach the surface, gradually warming things back up. But the story doesn't end with just these tiny particles floating in our stratosphere. Volcanoes also release enormous amounts of water vapor, and while water vapor is indeed a greenhouse gas that can trap heat, the story becomes beautifully complex when we consider what happens to all that water high in the atmosphere. Much of it eventually condenses and falls as precipitation, but not before it has interacted with other atmospheric components in ways that can actually enhance the cooling effect we've been discussing. There's something almost meditative about watching a volcanic plume rise into the sky. It starts as a dark column, often glowing at its base with the fire within, then spreads and flattens as it reaches the upper atmosphere, forming what volcanologists call an umbrella cloud. This spreading pattern isn't random, it's following the natural layers of our atmosphere, like smoke from a chimney hitting the ceiling of a room and spreading outward in all directions. To truly understand how volcanoes cool our planet, we need to take a gentle journey upward through the layers of Earth's atmosphere. Imagine we're in a hot air balloon, slowly rising from the ground level where we live and breathe. At first, as we climb through the troposphere, the lowest layer of atmosphere where all our weather happens, the temperature drops steadily. This is the realm of clouds and storms, of gentle breezes and fierce hurricanes. Most volcanic particles don't make it much beyond this layer, and those that do stay here get washed out fairly quickly by rain and snow. But the truly spectacular volcanic eruptions, the ones that make headlines around the world, send their particles much higher. As our imaginary balloon continues to rise, we encounter something remarkable. Around 6 to 10 miles above the Earth's surface, the temperature stops dropping and actually begins to rise again. We've entered the stratosphere, and this is where the real magic happens for volcanic climate influence. The stratosphere is like a vast, stable lake in the sky. Unlike the turbulent troposphere below, where air masses mix and churn constantly, the stratosphere is remarkably calm and stratified, hence its name. Air moves much more slowly here, often taking months or even years to complete a journey around the globe. For volcanic particles, this is perfect. Instead of being quickly washed out by rain or dispersed by storms, they can remain suspended for years, slowly spreading around the entire planet like a thin global veil. When Mount Pinatubo erupted in the Philippines in 1991, It provided scientists with a perfect natural laboratory to study this process. The eruption was large enough to inject significant amounts of sulfur dioxide into the stratosphere, yet it occurred during an era when we had satellites and advanced monitoring equipment to track exactly what happened. What they observed was like watching Earth put on a pair of sunglasses in slow motion. Within weeks of the eruption, the sulfur dioxide had spread halfway around the world. Within months, it had formed a complete band around the entire planet. The particles, now converted to tiny droplets of sulfuric acid, began their work as planetary air conditioners. Satellites measuring incoming solar radiation detected a measurable decrease in the amount of sunlight reaching Earth's surface. Ground-based temperature measurements began showing a slight but consistent cooling trend that lasted for several years. The cooling effect wasn't dramatic. We're talking about average global temperatures dropping by about 0.5 degrees Celsius. That might not sound like much, but consider this. The difference between our current climate and the Ice Age that ended about 10,000 years ago was only about 6 degrees Celsius. In climate terms, even small changes can have profound effects when they persist over long periods. What makes volcanic cooling so fascinating is how selective it can be. The tiny particles in the stratosphere are incredibly efficient at scattering certain wavelengths of light while allowing others to pass through relatively unchanged. They are particularly good at reflecting back the shorter wavelengths, the blues and violets, while allowing longer wavelengths like reds and oranges to continue on their journey to Earth's surface. This is why sunsets often become more spectacular in the months and years following major volcanic eruptions. The sky takes on deeper, more vivid hues as the volcanic particles act like a natural colour filter. But the effects go beyond just pretty sunsets. The reduced amount of solar energy reaching Earth's surface means less energy available to drive weather systems. This can lead to cooler summers, altered precipitation patterns, and shifts in seasonal timing that ripple through ecosystems around the world. Farmers might notice that growing seasons become slightly shorter, or that certain crops struggle in the reduced light conditions. Ocean temperatures might drop slightly, affecting marine ecosystems and fish populations. The beauty of this natural cooling system lies in its temporary nature. Unlike human-caused changes to atmospheric composition, volcanic particles don't accumulate indefinitely. They gradually settle out of the atmosphere, clump together into larger particles that fall as precipitation, or get broken down by chemical reactions with other atmospheric components. Within 2 to 5 years after even the largest eruptions, the atmosphere largely returns to its pre-eruption state. This temporary quality means that volcanic cooling acts more like a natural reset button than a permanent climate modification. When the Earth's climate system gets pushed in one direction, say toward warming, major volcanic eruptions can provide a temporary cooling influence that gives other natural systems time to respond and adjust. It's like having a pressure relief valve on a steam engine, preventing the system from building up too much energy in any one direction. History is filled with mysterious periods of cooling that puzzled generations of people who lived through them. Imagine living in the early 1800s, when summer seemed to forget to arrive. The year 1816 became known as the Year Without a Summer, a time when snow fell in June across New England, crops failed across Europe and North America, and people wrapped themselves in winter coats during what should have been the warmest months of the year. For those who experienced it, this strange summer must have felt like the world was ending. Farmers watched their crops wither in fields that should have been basking in warm sunshine. Children who had never seen snow except in winter found themselves building snowmen in early summer. The sun seemed dimmer, almost as if a veil had been drawn across the sky, filtering out its warmth and leaving behind an eerie twilight quality to daylight hours. What those people couldn't have known was that their strange cold summer was the result of something that had happened a year earlier and literally half a world away. On April 10, 1815, Mount Tambora in Indonesia had erupted with such violence that it ranks as one of the most powerful volcanic explosions in recorded human history. The sound of the eruption was heard over 200 miles away. Imagine thunder so loud it could be heard from New York to Miami. The explosion ejected so much material into the atmosphere that it created its own weather systems, and the ashfall was so heavy that it plunged areas hundreds of miles away into darkness for days. But the immediate local effects of the Tambora eruption, dramatic as they were, pale in comparison to its global impact. The eruption had injected an estimated 60 million tons of sulfur dioxide into the stratosphere, enough to create a thin but effective planetary sunscreen that persisted for years. As this sulfur dioxide converted to sulfuric acid droplets and spread around the globe, it began its work of intercepting incoming solar radiation, reducing the amount of energy available to warm Earth's surface. The effects rippled outward like stones dropped in a still pond, touching lives in ways both subtle and profound. In Europe, the unusually cold and wet weather led to widespread crop failures and famine. In China, the disrupted weather patterns contributed to flooding that affected millions of people. In North America, the failed harvests drove many farming families to abandon their homesteads and migrate westward in search of better growing conditions. Some historians even suggest that the westward expansion of the United States was accelerated by people fleeing the climate disruption caused by a volcano they had never heard of, located on an island they couldn't have found on a map. The Tambora cooling provides us with a perfect natural experiment in how volcanic climate modification works on a global scale. Unlike the complex, multiple factors that influence our climate today, the 1815 to 1816 cooling event can be traced directly to a single, well-documented volcanic eruption. It gives us a clear picture of how quickly volcanic particles can spread around the world and how long their effects can persist. But Tambora wasn't unique in human history. When we look back through historical records, we find other periods of mysterious cooling that correlate remarkably well with major volcanic eruptions. The year 1628 BCE saw a massive eruption of the volcano Thera in the Mediterranean, an event so catastrophic that it may have contributed to the collapse of the Minoan civilization and inspired the legend of Atlantis. Tree ring data from around the world shows evidence of reduced growth during this period, suggesting that the climate effects were felt globally. Even more intriguing are the clusters of volcanic eruptions that seem to have contributed to longer-term climate changes. During the late medieval period, a series of large volcanic eruptions combined with other factors to help usher in what historians call the Little Ice Age, a period from roughly 1300 to 1850 CE, when global temperatures were noticeably cooler than they had been for centuries before, or have been since. Picture Europe during this time. Rivers that rarely froze began freezing solid in winter, allowing people to hold frost fairs on the Thames River in London. Glaciers advanced down mountain valleys, swallowing up villages and farmland that had been cultivated for generations. Growing seasons shortened, forcing people to adapt their agriculture and sometimes abandon settlements that had thrived for centuries. The famous paintings of Dutch masters from this period often show people ice skating and enjoying winter festivals, but these weren't just artistic choices. They were documenting a reality of longer, colder winters that were partly the result of increased volcanic activity around the world. What makes these historical cooling periods so fascinating from a scientific perspective is how they demonstrate the power of volcanic climate modification to influence human civilization itself. The cooling following major eruptions didn't just make things a bit chillier, it changed the course of human history. Famines triggered by volcanic cooling contributed to social unrest and political upheaval. Migration patterns shifted as people sought more favourable climates. Artistic and cultural expressions reflected the reality of a world that seemed colder and darker than it had been for their grandparents. Yet for all their dramatic effects, these volcanic cooling periods also demonstrate something hopeful about our planet's climate system, its remarkable ability to recover and return to equilibrium. No matter how large the volcanic eruption, or how dramatic the cooling, the effects eventually fade as the volcanic particles settle out of the atmosphere. The climate system, like a pendulum disturbed from its rest position, eventually swings back toward its natural balance point. This recovery process isn't instantaneous. It can take years or even decades for the full effects of a major eruption to dissipate completely. But it does happen, driven by the same natural processes that created the cooling in the first place. The sulfuric acid droplets that block incoming sunlight gradually combine with other atmospheric particles, becoming heavy enough to fall back to Earth as precipitation. The stratospheric winds that spread the particles around the globe also gradually disperse them, reducing their concentration to the point where their climate effects become negligible. Imagine, if you will, stepping into a cathedral where rays of sunlight stream through stained glass windows, illuminating countless dust motes dancing in the air. Each tiny particle catches and scatters the light, creating an almost cool display of floating glowing specks. This is remarkably similar to what happens when volcanic particles interact with sunlight in our atmosphere, except the cathedral is the entire sky, and the dance of particles affects the climate of our entire planet. The particles that volcanoes inject into our atmosphere are almost impossibly small, so tiny that millions of them could fit on the period at the end of this sentence. These microscopic actors in our climate story are primarily composed of sulfuric acid and water, formed when sulfur dioxide gas from volcanic eruptions combines with water vapor and oxygen high in the stratosphere. But their diminutive size belies their enormous influence on how our planet interacts with energy from the sun. To understand how these particles work their cooling magic, we need to think about light itself. Sunlight appears white to our eyes, but its bulbs are actually composed of all the colours of the rainbow: red, orange, yellow, green, blue, indigo and violet, blended together. Each colour corresponds to a different wavelength of electromagnetic radiation, with red light having longer wavelengths and violet light having shorter ones. When this rainbow of light encounters a volcanic particle in the atmosphere, something beautiful and complex happens. The interaction between light and these tiny particles follows principles that scientists call scattering theory. Just as a pebble thrown into a pond creates circular ripples that spread outward, a particle in the atmosphere creates a complex pattern of scattered light waves. The size of the particle compared to the wavelength of the light determines exactly how this scattering occurs, and volcanic particles happen to be just the right size to be incredibly efficient at scattering shorter wavelengths, the blues and violets, while allowing longer wavelengths like reds and oranges to pass through more easily. This selective scattering is what gives us those spectacular sunsets following major volcanic eruptions. As sunlight passes through layers of volcanic particles in the atmosphere, much of the blue and violet light gets scattered away in other directions, while the reds and oranges continue on their journey to our eyes. The result is sunsets painted in colours so vivid and intense that they almost seem artificial, as if someone had adjusted the colour saturation on a photograph. But the climate cooling effect comes not from this beautiful colour filtering, but from the simple fact that when light gets scattered, much of it gets sent back towards space instead of continuing down to Earth's surface. Think of it like this. Imagine you're trying to pour water through a screen made of tiny holes. Some of the water makes it through, but some bounces off and doesn't reach what's below the screen. The volcanic particles act like a very fine screen for sunlight, allowing some energy through but reflecting a portion back to space. The amount of sunlight that gets reflected back to space by these particles is surprisingly substantial. During major volcanic eruptions, the reflectivity of Earth's atmosphere can increase by several %. That might not sound like much, but when you consider that we're talking about the energy output of the sun, enough to power human civilization millions of times over, even a small percentage change represents an enormous amount of energy that doesn't reach Earth's surface. Scientists have developed sophisticated ways to measure this scattering effect. Satellites orbiting high above our atmosphere can detect changes in the amount of solar radiation being reflected back to space. Ground-based instruments can measure how much sunlight reaches the surface at different wavelengths. Aircraft flying through volcanic clouds can sample the particles directly, analysing their size, composition, and concentration. All of this data comes together to create a detailed picture of how volcanic particles modify the flow of energy through our climate system. What emerges from all this scientific observation is a picture of remarkable efficiency. The volcanic cooling system works with elegant simplicity, tiny particles doing exactly what physics predicts they should do, with effects that scale up to influence the temperature of our entire planet. There are no complex feedback mechanisms or unpredictable interactions. The particles scatter light according to well-understood physical principles, reducing the amount of solar energy available to warm Earth's surface, and global temperatures respond accordingly. But perhaps the most fascinating aspect of this particle-light interaction is how it demonstrates the interconnectedness of processes operating on vastly different scales. Deep within the Earth, tectonic forces build pressure that eventually leads to volcanic eruptions. These eruptions release gases that form particles measuring nanometers across. These nanometer-scale particles interact with electromagnetic radiation from a star 93 million miles away. And this interaction between the infinitesimally small and the cosmically large influences weather patterns that affect billions of people across an entire planet. The particles themselves have lifespans that tell their own story of atmospheric circulation. Born in the violent heat of volcanic eruptions, they begin their existence as gas molecules that quickly transform into liquid droplets as they cool and rise through the atmosphere. In the stratosphere, they join the slow global circulation patterns that can take months or years to complete a journey around the world. During their atmospheric lifetime, each particle might scatter billions of photons of light, contributing to the global cooling effect while gradually growing larger through collision and combination with other particles. Eventually, as the particles grow too large to remain suspended in the thin air of the stratosphere, they begin their final journey downward. Some get incorporated into ice crystals in high-altitude clouds. Others simply grow heavy enough to fall through the atmosphere like invisible snow. By the time they reach the ground, they've completed a remarkable journey from the molten interior of our planet, through the middle atmosphere and back to the surface, having spent months or years serving as Earth's natural climate regulators. This cycle of creation, atmospheric residence, and eventual removal ensures that the volcanic cooling effect is always temporary. Unlike some human influences on climate that can persist for decades or centuries, volcanic particles clean themselves out of the atmosphere relatively quickly. This natural, self-limiting quality means that volcanic cooling provides a temporary cooling influence that allows other climate processes time to adjust and respond, rather than permanently altering the planet's energy balance. Now, let's take a gentle journey into the invisible world above our heads, where the real magic of volcanic cooling begins to unfold. Imagine, if you will, that the atmosphere is like a vast, three-dimensional ocean of air, with currents and layers as complex as any sea. When our volcanic friend releases its sulfur dioxide into this aerial ocean, something truly remarkable begins to happen. A slow, beautiful transformation that will ultimately touch every corner of our planet. Picture sulfur dioxide molecules as tiny, eager travelers, each one carrying 2 oxygen atoms alongside a single sulfur atom. These molecular wanderers rise through the atmosphere with purpose, lifted by the warm currents of volcanic gases and the natural circulation of air. They're remarkably patient, these little molecules, taking their time as they ascend through the lower atmosphere, past the clouds where commercial airplanes fly, higher and higher until they reach a special realm called the stratosphere. The stratosphere is a peaceful place, quite different from the turbulent lower atmosphere where weather happens. It's like a quiet library in the sky, where molecules can settle in for long conversations and gradual transformations. Here, about 20 to 30 kilometers above the ground, our sulfur dioxide molecules encounter something that will change their destiny forever. Tiny droplets of water vapor, so small they're more like whispers of moisture hanging in the crystalline air. What happens next is like watching a slow-motion dance of chemistry. The sulfur dioxide doesn't simply stay as it is. Oh no, it's far too social for that. Instead, it begins to react with the water vapor and oxygen in the stratosphere, undergoing a gentle transformation that takes weeks or even months to complete. Through this patient process, the sulfur dioxide gradually becomes sulfuric acid, but not the harsh, dangerous kind you might imagine. These are microscopic droplets so tiny that billions of them could dance on the head of a pin. These newly formed sulfuric acid droplets are the true heroes of our cooling story. They're incredibly small, much smaller than the particles in cigarette smoke, smaller even than most bacteria. Each droplet is like a perfectly crafted mirror, no bigger than a virus, designed by nature to perform one essential task: reflecting sunlight back to space with remarkable efficiency. As these microscopic mirrors accumulate in the stratosphere, they begin to form what scientists poetically call an aerosol layer. Don't let the technical term fool you. This is one of nature's most elegant inventions. Picture a thin, shimmering veil spread across the entire planet, so delicate and transparent that you would never notice it from the ground, yet so effective at reflecting solar radiation that it can cool the entire Earth by several degrees. The beauty of this system lies in its persistence. Unlike clouds in the lower atmosphere, which come and go with the weather, these stratospheric aerosols have staying power. They can linger in their lofty realm for 2, 3, even 4 years, continuously working to reflect away a portion of the sun's energy. It's as if the Earth has been gifted with a pair of elegant sunglasses, reducing the intensity of solar radiation just enough to provide relief from warming. But here's where the story becomes even more fascinating. The amount of cooling these volcanic aerosols can provide is truly impressive. When Mount Pinatubo erupted in 1991, for instance, it injected about 20 million tons of sulfur dioxide into the stratosphere. Over the following months, as this sulfur dioxide transformed into sulfuric acid aerosols, the global average temperature dropped by about 0.5 degrees Celsius. That might not sound like much, but in the delicate balance of Earth's climate system, it's equivalent to temporarily erasing decades of greenhouse gas warming. Think about that for a moment. A single volcanic eruption, lasting just a few days or weeks, created enough atmospheric cooling to counteract decades of human-caused warming. It's a humbling reminder of the immense power that lies sleeping beneath our feet, and the incredible sensitivity of our planet's climate system to even small changes in the amount of sunlight reaching the surface. The cooling effect doesn't happen overnight, though. Like all the best stories, this one unfolds gradually, with a beginning, middle, and end that span several years. In the first few months after a major eruption, scientists and weather watchers around the world begin to notice subtle changes. Sunsets become more vivid and colourful, painted in brilliant oranges and purples as sunlight filters through the new aerosol layer. The sun itself might appear slightly dimmed, as if viewed through a gentle filter. As months pass and the aerosol layer spreads and matures, the cooling effect reaches its peak. Weather patterns begin to shift in response to the reduced solar heating. Some regions might experience cooler summers, while others see changes in rainfall patterns or storm activity. It's as if the entire planet is adjusting to its new, slightly dimmed reality, like a house settling into comfortable shadows on a hot afternoon. The global nature of this cooling is particularly remarkable. Unlike local weather phenomena that affect only specific regions, volcanic aerosols in the stratosphere create a truly planetary response. The stratospheric winds carry these tiny mirrors around the entire globe within weeks of their formation, creating a uniform veil that reduces solar radiation everywhere. A volcano erupting in the Philippines can cool temperatures in Europe, North America, and Australia with equal effectiveness. Throughout Earth's long and storied history, there have been moments when volcanoes have flexed their ultimate cooling power, creating what we might call the Great Volcanic Winters. These are the times when the planet's internal fire has burned so intensely that it paradoxically plunged the world into extended periods of cold, demonstrating just how powerful the volcanic cooling mechanism can be when amplified to its extreme. Let's travel back in time, about 74,000 years ago, to witness one of the most dramatic examples of volcanic cooling in recent geological history. In what is now northern Sumatra, Indonesia, a supervolcano called Toba was stirring. Unlike the familiar cone-shaped volcanoes we often picture, Toba was something far more impressive and terrifying. A vast caldera, a collapsed volcanic crater dozens of kilometers across, filled with magma that had been building pressure for tens of thousands of years. When Toba finally erupted, it didn't simply blow its top like a cork from a champagne bottle. Instead, it essentially exploded, releasing more material into the atmosphere than any volcanic eruption in the past 2 million years. The amount of sulfur dioxide injected into the stratosphere was staggering, perhaps 1,000 times more than Mount Pinatubo would produce much later. The resulting aerosol layer was so dense and extensive that it created what scientists call a volcanic winter that lasted for years. Imagine for a moment what this must have been like for our early human ancestors. The sun, which had always been a reliable source of warmth and light, suddenly seemed weaker, filtered through a persistent haze that never quite cleared. Temperatures around the world plummeted by as much as 3 to 5 degrees Celsius, a massive shift that would have made tropical regions feel temperate and temperate regions feel arctic. The cooling was so severe and prolonged that it may have pushed humanity to the brink of extinction. Genetic evidence suggests that the global human population bottlenecked dramatically around this time, possibly falling to as few as a few thousand individuals worldwide. It's a sobering reminder of just how powerful volcanic cooling can be when unleashed at its full potential. But Toba wasn't the only supervolcano to demonstrate this cooling power. Throughout Earth's history, there have been other massive eruptions that have triggered similar planetary-scale cooling events. The Yellowstone supervolcano, which sits quietly beneath the beautiful national park in the western United States, has erupted catastrophically several times in the past 2 million years, each time creating massive cooling effects that lasted for decades. These great volcanic winters teach us something profound about the relationship between fire and ice, heat and cold. They show us that sometimes the most effective way to cool something down is to make it very, very hot first. It's like the Earth's own version of a fever, intense burst of heat that ultimately leads to a prolonged period of cooling and recovery. Even smaller eruptions throughout history have created notable cooling effects that have all shaped human civilization in ways we're only beginning to understand. The eruption of Mount Tambora in Indonesia in 1815, for example, was significant enough to create what became known as the Year Without a Summer in 1816. Across the Northern Hemisphere, temperatures were so depressed that crops failed, snow fell in summer months, and famine spread across many regions. This wasn't just a scientific curiosity, it was a human tragedy that affected millions of lives. But it also demonstrated something remarkable about the Earth's climate system. A single volcanic eruption on a remote Indonesian island managed to alter weather patterns across the entire globe, affecting harvests in New England, creating unusual storms in Europe, and changing monsoon patterns in Asia. It was as if the planet had been connected by an invisible web of atmospheric circulation, and pulling on one strand sent vibrations throughout the entire system. The Tambora eruption also gave us one of the most beautiful and haunting artistic records of volcanic cooling. The unusual atmospheric conditions created by the aerosol layer produced some of the most spectacular sunsets in recorded history, with brilliant reds and oranges that inspired painters across Europe. The famous painter J.M.W. Turner created some of his most memorable sunset paintings during this period, unknowingly documenting the optical effects of volcanic aerosols in the stratosphere. These historical examples help us understand that volcanic cooling isn't just a theoretical concept, it's a real and powerful force that has shaped our planet's climate and human history for millions of years. The same mechanisms that created the Year Without a Summer are still operating today, every time a volcano releases sulfur dioxide into the stratosphere. The scale might be different, but the fundamental physics remains the same. What's particularly fascinating is how these volcanic winters demonstrate the incredible sensitivity of Earth's climate system. A relatively small change in the amount of sunlight reaching the surface, just a few %, can trigger dramatic shifts in temperature, weather patterns, and ecosystem behavior. It's a reminder that our planet's climate is like a finely tuned instrument, responsive to even subtle changes in the energy balance between incoming solar radiation and outgoing heat. This sensitivity also explains why volcanic cooling has been such an important factor in Earth's climate history. Over geological timescales, volcanic activity has varied significantly, with some periods seeing much more intense and frequent eruptions than others. During times of high volcanic activity, the cumulative cooling effect of multiple eruptions could help moderate global temperatures, while during quiet periods, the absence of volcanic cooling might allow other warming factors to have greater influence. To truly appreciate how volcanoes cool our planet, we need to understand the intimate dance between particles and light that takes place every day in the atmosphere above our heads. It's a performance that began billions of years ago and continues every moment, invisible to our eyes, but fundamental to the climate we experience on Earth's surface. Let's start by imagining light itself, not as we normally think of it, as something we simply see with our eyes, but as a stream of energy packets called photons, each one carrying a specific amount of solar energy from our star to our planet. These photons have travelled across 93 million miles of empty space, a journey that takes just over 8 minutes, carrying with them the power that drives our weather, grows our plants, and warms our world. When these solar photons encounter the tiny sulfuric acid droplets created by volcanic eruptions, something magical happens. The droplets act like microscopic disco balls, scattering the light in all directions, but unlike a disco ball that reflects light randomly, these volcanic aerosols have a particular talent. They're especially good at scattering light backward, sending it right back towards space from whence it came. This backward scattering is crucial to understanding volcanic cooling. Imagine sunlight as a gentle rain of energy falling toward the Earth. Under normal circumstances, most of this energy rain would reach the surface, where it would be absorbed by oceans, land, and vegetation warming our planet. But when volcanic aerosols are present in the stratosphere, they act like a million billion tiny umbrellas, deflecting a portion of this energy rain back to space before it can reach the ground. The physics behind this scattering is elegantly described by something called Meyer scattering, named after the German physicist Gustav Meyer, who first explained how particles scatter light. The volcanic aerosol droplets are just the right size, typically between 0.1 and 1 micrometer in diameter, to be incredibly efficient at scattering visible sunlight. They are like nature's own perfect mirrors, engineered by atmospheric chemistry to reflect solar radiation with remarkable effectiveness. But here's where the story becomes even more interesting. These aerosol particles don't scatter all colours of light equally. They're particularly effective at scattering shorter wavelengths, the blues and violets, while allowing longer wavelengths like reds and oranges to pass through more easily. This selective scattering is what creates those spectacular orange and red sunsets that often follow major volcanic eruptions. The blue light gets scattered away in all directions by the aerosols, while the reds and oranges continue on their path to our eyes, creating skies painted in warm, rich colours. This selective scattering also explains why the sun itself might appear dimmed or reddened when viewed through a layer of volcanic aerosols. It's not that the sun is actually producing less light, it's that the blue and green components of sunlight are being scattered away before they reach our eyes, leaving behind the warmer colours that can penetrate through the aerosol layer more easily. The cooling effect of this light scattering is directly proportional to how much sunlight gets sent back to space. Scientists measure this using something called radiative forcing, essentially how much the energy balance of Earth is altered by the presence of the aerosols. A typical major volcanic eruption might create a radiative forcing of -2 or 3 watts per square meter, meaning that every square meter of Earth's surface receives 2 or 3 watts less solar energy than it normally would. That might not sound like much, but when you multiply it by the entire surface area of our planet, it adds up to an enormous amount of energy. It's equivalent to dimming the sun by about 1%, which is more than enough to cool global temperatures by several degrees over the years that the aerosols remain in the stratosphere. The longevity of these aerosols in the stratosphere is crucial to their cooling effect. Unlike particles in the lower atmosphere, which get washed out by rain within days or weeks, stratospheric aerosols can persist for years because the stratosphere is remarkably dry and stable. There's very little weather activity up there, no storms, no rain, no turbulent mixing that would quickly remove the particles. Instead, the aerosols settle very slowly under the gentle influence of gravity, gradually growing larger as they collide and merge with each other. This slow settling process, combined with the lack of precipitation to wash them out, means that a single major volcanic eruption can influence global climate for 3 to 5 years or even longer. During this extended period, the aerosols continue their patient work of scattering sunlight back to space. They don't take breaks or holidays. Every photon that encounters them has a chance of being redirected away from Earth. It's this relentless, continuous action that creates the sustained cooling effect we observe after major volcanic eruptions. The global distribution of this cooling effect is also remarkable. Because the stratospheric winds circulate around the entire planet relatively quickly, volcanic aerosols from a single eruption can create cooling effects that are felt worldwide within months. A volcano in Indonesia can cool temperatures in Europe and North America with almost equal effectiveness, demonstrating the truly global nature of atmospheric circulation. This global distribution happens because of the unique characteristics of stratospheric circulation. Unlike the chaotic, turbulent mixing of the lower atmosphere where weather occurs, the stratosphere has more organized, large-scale circulation patterns. The aerosols get caught up in these circulation patterns and are transported around the globe, creating a relatively uniform layer that affects solar radiation everywhere. The efficiency of this global distribution system is truly remarkable. Within just a few weeks of a major eruption, sensitive instruments can detect the presence of volcanic aerosols at monitoring stations around the world. Within a few months, the aerosol layer has become so well mixed that it provides relatively uniform cooling effects at all longitudes around the globe. In our modern era, we've been fortunate, or perhaps unfortunate, depending on your perspective, to witness several dramatic demonstrations of volcanic cooling in real time, with all the sophisticated instruments and global monitoring networks that allow us to study these phenomena in unprecedented detail. These recent eruptions have served as natural laboratories, helping us understand exactly how volcanoes cool the planet and providing crucial data for climate scientists around the world. The most famous and well-studied example in recent decades was the eruption of Mount Pinatubo in the Philippines in June 2019. This wasn't just any volcanic eruption, it was the second largest eruption of the 20th century, and it occurred at a time when our global monitoring capabilities were advanced enough to track its effects with remarkable precision. Picture the scene. Mount Pinatubo had been quiet for over 600 years, its slopes covered in lush tropical vegetation, its summit crowned with what appeared to be a peaceful, dormant crater. Local communities had lived on its fertile slopes for generations, growing rice and other crops in the rich volcanic soil, largely unaware that beneath their feet lay one of the world's most powerful sleeping giants. But in the spring of 1991, the giant began to stir. Small earthquakes started occurring beneath the mountain, increasing in frequency and intensity over several weeks. Steam began venting from new fractures near the summit. Scientists from around the world rushed to the Philippines to monitor what was clearly becoming a potentially massive eruption. When Pinatubo finally erupted on June 15, 1991, it did so with spectacular force. The eruption column rose to heights of over 35 kilometers, well into the stratosphere, carrying with it an estimated 20 million tons of sulfur dioxide. To put that in perspective, imagine every car, truck and bus on Earth running continuously for several years. That's roughly equivalent to the amount of sulfur dioxide that Pinatubo injected into the atmosphere in just a few hours. But here's what made Pinatubo so valuable for scientific study. We were watching. Satellites tracked the spread of the sulfur dioxide plume as it circled the globe. Ground-based instruments measured the gradual transformation of sulfur dioxide into sulfuric acid aerosols. Temperature monitoring stations around the world recorded the slow but steady decline in global average temperatures over the following months and years. The results were exactly what volcanic cooling theory predicted, but seeing it happen in real time was still breathtaking. Within weeks of the eruption, the sulfur dioxide had spread around the entire globe, forming a band of aerosols that encircled the Earth like a shimmering belt. Sunsets became more brilliant and colourful worldwide as the aerosols scattered blue light and allowed reds and oranges to dominate the evening sky. More importantly for our understanding of climate, global temperatures began to drop. The cooling wasn't immediate. It took several months for the full effect to develop as the sulfur dioxide completed its transformation into reflective aerosols. But by 1992 and 1993, global average temperatures were running about half a degree Celsius cooler than they would have been without the eruption. Half a degree might not sound like much, but in the context of global climate, it's enormous. To put it in perspective, the entire warming from human greenhouse gas emissions since the Industrial Revolution amounts to about 1 degree Celsius. Pinatubo's cooling effect was equivalent to temporarily erasing 50 years of human-caused warming. It was as if someone had installed a global air conditioning system that ran for 3 solid years. The Pinatubo eruption also provided scientists with invaluable insights into how volcanic cooling affects different aspects of the climate system. The reduced solar radiation didn't just lower temperatures, it also affected precipitation patterns, storm activity, and even the behaviour of the El Niño and La Niña climate cycles in the Pacific Ocean. It was a vivid demonstration of how interconnected Earth's climate system really is. But Pinatubo wasn't the only recent example of volcanic cooling. In 1982, El Chichon in Mexico erupted with similar force, also injecting millions of tons of sulfur dioxide into the stratosphere. Like Pinatubo, El Chichon created a measurable cooling effect that lasted for several years, providing additional confirmation of the volcanic cooling mechanism. More recently, the 2010 eruption of Eyjafjallajökull in Iceland provided a different perspective on volcanic impacts. While this eruption was much smaller than Pinatubo and didn't create significant global cooling, it demonstrated how even moderate volcanic activity can affect regional climate and, more famously, disrupt global air travel for weeks. These modern examples have been invaluable for scientists studying volcanic cooling because they provide real-world validation of theoretical models. Before we had the opportunity to observe major eruptions with modern instruments, much of our understanding was based on historical records and indirect evidence. Events like Pinatubo allowed researchers to test their theories against actual measurements, refining our understanding of how volcanic aerosols behave in the stratosphere and how effectively they reflect sunlight. The data collected from these eruptions has also helped scientists better understand the relationship between the size of an eruption and the magnitude of its cooling effect. Not all volcanic eruptions cool the planet equally. The key factor is how much sulfur dioxide reaches the stratosphere, not necessarily how much total material is erupted. A relatively small eruption that injects sulfur-rich gases high into the stratosphere can have a much greater cooling effect than a much larger eruption that doesn't reach the stratosphere. This insight has important implications for understanding Earth's climate history and predicting future volcanic impacts. It means that the cooling power of ancient eruptions can't simply be estimated from the volume of material they produced. Scientists also need to understand the sulfur content of the magma and how high the eruption columns reached. Perhaps most importantly, these modern observations have given us a deep appreciation for the speed and global reach of volcanic cooling effects. In our interconnected world, the idea that a single volcanic eruption in one country can affect weather patterns worldwide within weeks is both fascinating and humbling. It reminds us that Earth's atmosphere is truly a global system, where events in one location can have consequences that ripple around the entire planet. The study of these recent eruptions has also highlighted the temporary nature of volcanic cooling. Unlike greenhouse gases, which can remain in the atmosphere for decades or centuries, volcanic aerosols have a relatively short lifespan. The cooling effect peaks within a year or two of the eruption and then gradually fades as the aerosols settle out of the stratosphere. This temporary nature is both a limitation and an advantage. It means volcanic cooling can't provide long-term climate mitigation, but it also means the effects are reversible and don't accumulate over time. Let me take you back to a time when the world held its breath, when the very air seemed to shimmer with an otherworldly light, and when farmers across the globe looked up at skies that had forgotten how to behave. It was 1815, and somewhere in the distant Indonesian archipelago, Mount Tambora was preparing to remind humanity just how small we truly are in the grand theatre of our planet's power. Picture, if you will, a mountain that had stood sentinel over the Sumbawa island for millennia. Tambora was not just any volcano. It was a giant rising over 14,000 feet into the tropical sky. Its peak crowned with lush vegetation, and its slopes home to countless communities who had learned to live in harmony with this sleeping giant. The people of Sumbawa had no way of knowing that beneath their feet, deep in the earth's restless woolly heart, pressure was building to levels that would soon reshape not just their island, but the entire world's climate. On the evening of April the 10th, 1815, Tambora began to stir. The first rumblings were heard hundreds of miles away, like distant thunder that seemed to roll endlessly across the horizon. But this was no ordinary storm. This was the earth itself, speaking in a voice so powerful that it would be heard around the world. When Tambora finally erupted, it did so with a violence that defies easy description. The sound of the explosion travelled over 200 miles, reaching the island of Sumatra, where startled residents thought they were hearing cannon fire from some distant naval battle. But the sound was just the beginning. What followed was something that would demonstrate, perhaps more clearly than any event in recorded history, just how profoundly volcanoes can influence our planet's climate. Tambora didn't just erupt, it quite literally blew its top off, hurling an estimated 38 cubic miles of rock, ash and debris into the atmosphere. To put this in perspective, imagine taking a mountain the size of Mount Fuji and launching it entirely into space. That's the scale of material that Tambora ejected in just a few days of explosive fury. As the massive eruption column rose into the stratosphere, reaching heights of over 25 miles above the Earth's surface, it carried with it something that would prove far more significant than all the rock and ash combined. Mixed within that towering column of debris were millions of tons of sulfur dioxide, the same compound we've been exploring in our gentle journey through volcanic chemistry. But the scale of Tambora's sulfur release was unprecedented in human history. It was as if the Earth had opened a massive chemical factory and released the contents of decades' worth of production in a single week. The sulfur dioxide from Tambora didn't just disperse randomly into the atmosphere. Instead, it followed the same elegant dance we've discussed before, but on a scale that would transform the entire planet's climate system. As the gas reached the stratosphere, it began its slow transformation into sulfuric acid droplets, forming aerosols that would create a veil around the entire Earth. But this wasn't the localized cooling effect we might see from a smaller eruption. This was a global dimming event that would last for years. The aerosol veil that formed in the months following Tambora's eruption was so dense and widespread that it literally changed the colour of sunsets around the world. People in London reported seeing sunsets of the most extraordinary hues, deep purples, brilliant oranges, and red so intense they seemed almost artificial. The famous artist J.M.W. Turner was so inspired by these atmospheric effects that he painted some of his most celebrated works during this period, capturing skies that seemed to glow with an inner fire. But the beautiful sunsets were just the visible manifestation of something far more profound happening to our planet's energy balance. The sulfuric acid aerosols were acting like a massive mirror in the sky, reflecting sunlight back to space before it could reach the Earth's surface. Scientists estimate that Tambora's aerosol cloud reduced the amount of solar radiation reaching the Earth by approximately 3 watts per square meter globally, a seemingly small number that would have enormous consequences for the world's climate system. The cooling effect began to manifest in ways that would earn 1816 the ominous nickname, the year without a summer. Across the Northern Hemisphere, temperatures dropped by an average of 1 to 2 degrees Celsius, but the impact was far from uniform. Some regions experienced temperature drops of 5 degrees or more, while unusual weather patterns created chaos in agricultural systems that had evolved over thousands of years. In New England, frost occurred in every month of 1816, even during what should have been the warmest summer days. Farmers watched in despair as their crops withered and died, not from drought or disease, but from the simple absence of the sun's warming rays. The growing season was shortened by weeks, and in some areas it seemed as though summer had been cancelled entirely. Snow fell in June across much of the northeastern United States, and ice formed on ponds and lakes during what should have been the height of the warm season. But perhaps nowhere was the effect more dramatic than in Europe, where the climate disruption triggered what historians now recognise as one of the worst famines in modern European history. The combination of cold temperatures and altered precipitation patterns created perfect conditions for crop failures across the continent. In Ireland, the potato harvest failed, presaging the devastating famines that would plague the country in later decades. In Switzerland, the grain harvest was so poor that the government had to ban the feeding of grain to livestock in order to preserve food for human consumption. The climate effects of Tambra reached far beyond simple temperature changes. The altered atmospheric conditions disrupted monsoon patterns across Asia, leading to flooding in some regions and drought in others. In China, the normally reliable summer rains failed in many provinces, while other areas experienced unprecedented flooding. The carefully balanced agricultural systems that had fed millions for generations were thrown into chaos by the invisible hand of volcanic aerosols circling the globe, tens of thousands of feet above. One of the most fascinating aspects of Tambra's climate impact was how it demonstrated the interconnectedness of our global climate system. The aerosols didn't just affect the regions directly downwind from the volcano, they spread throughout the entire stratosphere, creating a global cooling effect that lasted for several years. This was nature's own experiment in what scientists today call solar radiation management, showing us exactly what happens when we reduce the amount of sunlight reaching the Earth's surface. The story of Tambra also reveals something profound about the relationship between volcanoes and human civilization. The cooling effect of the eruption didn't just change weather patterns, it reshaped human history in ways that are still being understood today. The crop failures and famines that followed the eruption triggered mass migrations, as people fled regions where traditional agriculture was no longer viable. In the United States, the poor harvests in New England contributed to the westward migration that would define much of American history in the 19th century. The economic impacts were equally profound. The disruption to global food systems led to the first truly global food crisis of the modern era, with prices for grain and other staples skyrocketing around the world. In some regions, the price of wheat increased by 500% or more, leading to social unrest and political upheaval. The French Revolution had ended just decades before, but the memory of how food shortages could topple governments was still fresh in the minds of European leaders. Perhaps most remarkably, the year without a summer also became a catalyst for innovation and creativity. The gloomy, cold summer of 1816 kept many people indoors, leading to a burst of artistic and literary activity. It was during this strange, sun-starved summer that Mary Shelley wrote Frankenstein, inspired partly by the apocalyptic atmosphere created by Tambora's atmospheric effects. Lord Byron, trapped indoors by the unusual weather, penned some of his most famous poems during this period. The volcano's influence on human culture was as profound as its impact on climate. The story of Tambra, remarkable as it is, represents just one note in a much longer symphony of volcanic climate effects that have shaped our planet's history. As we sit here together, exploring these gentle giants of geological time, it's worth remembering that volcanic cooling is not just a historical curiosity, It's an ongoing process that has been influencing our planet's climate for millions of years, creating a rhythm of warming and cooling that has helped shape the very evolution of life on Earth. Let me guide you through some of the other major volcanic cooling events that have left their mark on human history, each one a testament to the profound power of these natural climate control systems. Each eruption tells us something new about how volcanoes can cool our planet, and together they paint a picture of a world where the solid Earth beneath our feet is in constant, though usually gentle, conversation with the atmosphere above. Take, for instance, the eruption of Laki in Iceland in 1783. This wasn't a single explosive event like Tambora, but rather a fissure eruption that lasted for 8 months, quietly but persistently releasing volcanic gases into the atmosphere. The Laki eruption was different from Tambora in many ways. It was less explosive, but it was more sustained, creating a continuous stream of sulfur dioxide that would eventually have climate effects rivaling those of much larger eruptions. The Laki eruption produced what scientists call a dry fog that spread across Europe and beyond. This wasn't the familiar fog of water droplets that we might see on a misty morning, but rather a haze of sulfuric acid particles that made the air itself seem thick and oppressive. The fog was so persistent and widespread that it was noticed and recorded by observers across Europe, who described air that seemed to shimmer with an unnatural light and sunsets that glowed with an eerie intensity. The cooling effect of Laki was felt most acutely in the winter of 1783 to 1784, which became one of the coldest on record in Europe and North America. In France, the severe winter contributed to the hardships that would eventually lead to the French Revolution. The connection between volcanic cooling and human history becomes clear when we consider that the poor harvests and economic disruption caused by climate anomalies often set the stage for social and political upheaval. But Laki's story also illustrates something fascinating about volcanic cooling effects. They don't always follow the same pattern. While Tambora's effects were most pronounced in the year immediately following the eruption, Laki's impact was more gradual and sustained. The continuous release of sulfur dioxide over 8 months created a persistent cooling effect that lasted for several years, demonstrating that volcanoes can influence climate in many different ways depending on the nature of their eruptions. Moving further back in time, we encounter the eruption of Huayna Putina in Peru in 1600. This eruption, less well known than Tambora but equally significant in its climate effects, injected massive amounts of sulfur dioxide into the stratosphere, creating cooling effects that were felt around the world. The eruption occurred during a period when detailed weather records were just beginning to be kept in many parts of the world, but the evidence of its impact can be found in everything from tree ring data to historical accounts of unusual weather. The Huayna Putina eruption contributed to what is now known as the Little Ice Age, a period of cooler temperatures that lasted from roughly 1550 to 1850. This wasn't a true ice age in the geological sense, but rather a period of distinctly cooler global temperatures that affected agriculture, human migration patterns, and even art and literature. The Little Ice Age was likely caused by a combination of factors, including reduced solar activity and several major volcanic eruptions, but Huayna Putina was one of the most significant contributors to this extended period of cooler climate. The cooling effects of Huayna Putina were felt most dramatically in the Northern Hemisphere, where the eruption coincided with some of the coldest summers on record. In Russia, the growing season was shortened so dramatically that famine became widespread, leading to social unrest and political instability. The connection between volcanic cooling and human society becomes even more apparent when we consider that the time of troubles in Russian history, a period of civil war and political chaos, occurred during the same period as the most intense cooling effects from Huayna Putina. One of the most remarkable aspects of these historical volcanic cooling events is how they reveal the global nature of our climate system. A volcano erupting in Indonesia could affect weather patterns in Europe, while an eruption in Peru could influence growing seasons in North America. This interconnectedness reminds us that our planet's climate is truly a global system, where events in one part of the world can have far-reaching consequences for the entire planet. But perhaps the most intriguing aspect of these historical examples is what they tell us about the relationship between natural climate variability and human civilization. Each major volcanic cooling event has left its mark not just on the climate record, but on human history as well. The crop failures, famines, and social upheavals that followed these eruptions remind us that climate and human society are intimately connected in ways that we're only beginning to fully understand. The study of these historical eruptions has also revealed something fascinating about the resilience of both natural and human systems. While volcanic cooling events can certainly disrupt climate patterns and human activities, they also demonstrate the remarkable ability of both ecosystems and societies to adapt to changing conditions. The cooling effects of even the largest eruptions are temporary on geological timescales, lasting only a few years at most, and both natural and human systems have evolved mechanisms for coping with these periodic disruptions. In the natural world, we see evidence of this resilience in the way ecosystems respond to volcanic cooling events. While the immediate effects can be dramatic, crop failures, changes in precipitation patterns, and shifts in temperature, ecosystems have evolved over millions of years with these periodic disruptions as a normal part of their environment. Plants and animals have developed strategies for surviving short-term climate anomalies, from seed banks that can survive years of poor growing conditions to migration patterns that allow species to move to more favourable habitats during periods of climate stress. Human societies too have shown remarkable adaptability in the face of volcanic cooling events. The famines and hardships that followed major eruptions often led to innovations in agriculture, food storage, and social organisation. The experience of surviving these climate disruptions has contributed to the development of more resilient food systems, better understanding of weather patterns, and stronger social networks for mutual support during times of crisis. The historical record of volcanic cooling events also provides us with valuable insights into how our climate system responds to changes in the amount of solar radiation reaching the Earth's surface. The natural experiments provided by major eruptions have helped scientists understand the sensitivity of our climate system to changes in the Earth's energy balance, information that is crucial for understanding both natural climate variability and the potential effects of human activities on our planet's climate. One of the most striking aspects of these historical examples is how they demonstrate the temporary nature of volcanic cooling effects. While the immediate impacts can be severe, lasting for several years, the climate system eventually returns to its pre-eruption state as the volcanic aerosols are gradually removed from the atmosphere. This temporary nature of volcanic cooling stands in contrast to other types of climate change, which can persist for much longer periods. As we continue our gentle exploration of how volcanoes cool our planet, let's turn our attention to something truly magical: the intricate dance of particles that occurs high above our heads in the stratosphere. It's here in this rarefied realm between Earth and space that the most dramatic cooling effects of volcanic eruptions play out in slow, elegant choreography that can last for years. Imagine, if you will, the stratosphere as a vast ballroom stretching from about 10 to 50 kilometers above the Earth's surface. This is a realm of extremes, temperatures that can drop to minus 80 degrees Celsius, air so thin that it contains only a tiny fraction of the molecules we breathe at sea level, and an environment so stable that once particles enter this realm, they can remain suspended for years, slowly circling the globe like dancers in an eternal waltz. When a powerful volcanic eruption sends its column of ash and gas soaring into this stratospheric ballroom, something remarkable begins to happen. The sulfur dioxide gas that we've been following on its journey from the volcano's magma chamber finally reaches the stage, where it will perform its most important role in cooling our planet. But this transformation doesn't happen instantly. It's a gradual process that unfolds over weeks and months, as chemistry and physics work together to create the particles that will eventually reflect sunlight back to space. The first step in this transformation occurs when the sulfur dioxide gas encounters the thin, cold air of the stratosphere. Here, in this hostile environment, the gas begins to react with the tiny amounts of water vapor that exist even at these extreme altitudes. The reaction is slow and gentle, nothing like the violent explosions that sent the gas skyward in the first place. Instead, it's a quiet chemical dance, as sulfur dioxide molecules link up with water molecules to form sulfuric acid. But even this is just the beginning of the story. The sulfuric acid that forms in the stratosphere doesn't remain as a gas. Instead, it begins to condense into tiny droplets, so small that they're measured in nanometers. These droplets are incredibly tiny, so small that millions of them could fit on the head of a pin. Yet despite their minuscule size, they possess the power to influence the climate of our entire planet. The formation of these aerosol particles is a delicate process, influenced by temperature, humidity, and the presence of other particles that can serve as nucleation sites. Think of it like the formation of raindrops in a cloud. The water vapor needs something to condense onto, a tiny particle or impurity that can serve as the seed for a larger droplet. In the stratosphere, this process is even more refined, as the extreme conditions mean that only the most stable particle configurations can survive. As these sulfuric acid droplets form and grow, they begin to exhibit the optical properties that make them so effective at cooling our planet. The droplets are just the right size to scatter sunlight very efficiently. They're large enough to interact with visible light, but small enough to remain suspended in the atmosphere for extended periods. This size range, typically between 0.1 and 1 micrometer, represents a sort of sweet spot for reflecting solar radiation back to space. The scattering process itself is governed by the same physical principles that make the sky blue and sunsets red. When sunlight encounters these tiny droplets, it bounces off in all directions, but the efficiency of this scattering depends on the wavelength of the light and the size of the particles. The sulfuric acid aerosols are particularly effective at scattering shorter wavelengths of light, the blues and violets that carry more energy, while allowing longer wavelengths like reds and oranges to pass through more easily. This selective scattering is what creates the spectacular sunsets that often follow major volcanic eruptions. The aerosols preferentially scatter away the blue light, leaving the longer wavelengths to reach our eyes and create those intense orange and red hues that have inspired artists and poets for centuries. But more importantly for our planet's climate, this scattering process is removing energy from the solar radiation that would otherwise reach the Earth's surface. The aerosols don't just scatter light randomly, they create what scientists call a radiative forcing effect, systematically reducing the amount of solar energy that reaches the Earth's surface. This forcing is remarkably efficient. Studies have shown that the aerosols from a single major eruption can reduce global average temperatures by 0.5 to 1 degree Celsius, and in some cases even more. This might not sound like much, but on a global scale, it represents an enormous amount of energy, equivalent to reducing the sun's brightness by a small but significant amount. The beauty of this aerosol cooling system lies in its global reach. Unlike other climate effects that might be localized to specific regions, the stratospheric aerosols from major volcanic eruptions spread throughout the entire global atmosphere. The stratosphere has unique circulation patterns that can transport particles from one hemisphere to another, creating a truly global cooling effect that can influence weather patterns on every continent. This global distribution happens because of the stratosphere's peculiar circulation patterns. Unlike the turbulent mixing that occurs in the lower atmosphere, the stratosphere has a much more ordered circulation system. Particles injected into the stratosphere in one location can be transported by these circulation patterns to other parts of the globe, creating a relatively uniform global layer of aerosols. This is why eruptions in the tropics, like Tambora, tend to have more global impact than eruptions at higher latitudes. The tropical stratosphere is more effectively connected to the global circulation system. The lifetime of these aerosols in the stratosphere is another crucial factor in their climate impact. Unlike particles in the lower atmosphere, which can be washed out by rain or removed by other processes within days or weeks, stratospheric aerosols can remain suspended for years. The average residence time for sulfuric acid aerosols in the stratosphere is typically 1 to 3 years, depending on the altitude at which they are injected and the specific circulation patterns at the time of the eruption. During this extended residence time, the aerosols continue to evolve and change. They can grow larger through coagulation, smaller particles sticking together to form larger ones, or they can shrink through evaporation. The particles also gradually settle out of the stratosphere, slowly descending back toward the lower atmosphere, where they can eventually be removed by precipitation. This gradual removal process means that the cooling effect of a major eruption doesn't end abruptly, but rather fades gradually over a period of several years. The efficiency of this aerosol cooling system has led some scientists to propose it as a potential solution to human-induced climate change, a technique called stratospheric aerosol injection. By artificially injecting sulfur compounds into the stratosphere, we could potentially mimic the cooling effects of volcanic eruptions, providing a temporary reprieve from global warming. However, this approach would come with significant risks and uncertainties, reminding us that while volcanic cooling is a natural process that has been occurring for millions of years, deliberately manipulating our planet's climate system is a much more complex and potentially dangerous undertaking. The study of volcanic aerosols has also revealed fascinating details about the complex interactions between different components of our climate system. The aerosols don't just affect temperature, they can also influence precipitation patterns, atmospheric circulation, and even the chemistry of the atmosphere itself. For example, the presence of sulfuric acid aerosols can affect the formation and properties of clouds, creating cascading effects throughout the climate system that we're only beginning to understand. As we contemplate this elegant dance of particles high above our heads, it's worth reflecting on the remarkable fact that events occurring in the stratosphere, a realm so remote from our daily experience that most of us will never visit it, can have such profound effects on the climate we experience at the Earth's surface. The aerosols from a single volcanic eruption, particles so tiny that they're invisible to the naked eye, can collectively alter the energy balance of our entire planet, demonstrating once again the interconnected nature of our Earth system and the profound ways in which geological processes can influence the climate that sustains all life on our planet. In the quiet corners of space hundreds of miles above our heads, silent sentinels drift through the cosmic darkness. These are our modern guardians, the satellites that watch over Earth's volcanoes with an unblinking gaze. It's a beautiful marriage of technology and nature, where cutting-edge instruments peer down through the atmosphere to witness the ancient dance of fire and ice that has shaped our planet for billions of years. Imagine, if you will, sitting in a comfortable chair by a window, watching the gentle movements of clouds across the sky. Now picture that same peaceful observation, but from space, where satellites equipped with sensitive instruments can detect the slightest changes in temperature, the faintest whispers of gas emissions, and the subtlest shifts in a volcano's breathing patterns. This is how we've learned to listen to the Earth's heartbeat from afar. The story of satellite volcanic monitoring began in the 1960s, when the first weather satellites started sending back images of our planet. Scientists quickly realized that these eyes in the sky could see things that ground-based observers might miss. A volcanic eruption viewed from space reveals its secrets in ways that would be impossible to detect from the surface. The thermal signatures, the spreading patterns of ash clouds, the way volcanic gases interact with sunlight. All of these become visible when you step back far enough to see the bigger picture. One of the most remarkable aspects of satellite monitoring is how it reveals the cooling effects of volcanoes in real time. When Mount Pinatubo erupted in 1991, satellites watched as massive amounts of sulfur dioxide shot into the stratosphere, creating a veil that would cool the planet for years to come. The instruments could track the movement of this cooling veil as it spread around the globe, measuring its thickness, its chemical composition, and its interaction with sunlight. It was like watching a slow-motion movie of the Earth putting on a protective blanket. The technology has become so sophisticated that satellites can now detect volcanic unrest long before any visible signs appear on the surface. They measure the heat emanating from volcanic regions, track the movement of underground magma by detecting tiny changes in the Earth's surface, and monitor the chemical composition of gases being released from volcanic vents. It's as if we've given ourselves the ability to take the Earth's temperature and listen to its breathing, all from the peaceful vantage point of space. Consider the gentle persistence of the Terra satellite, launched in 1999 as part of NASA's Earth Observing System. Terra carries an instrument called MODIS, the Moderate Resolution Imaging Spectroradiometer, which sounds complex but performs a beautifully simple task. It measures the heat radiating from Earth's surface in multiple wavelengths of light, creating detailed thermal maps that reveal volcanic activity. When a volcano begins to stir, even subtly, MODIS can detect the increased heat signature, often weeks or months before any dramatic eruption occurs. The beauty of this system lies in its quiet efficiency. Every day, as Terra completes its orbit around Earth, MODIS captures thousands of images, each one a snapshot of our planet's thermal activity. These images are processed by computers that have been trained to recognize the subtle patterns that indicate volcanic unrest. It's like having a team of patient observers, never sleeping, never missing a detail, always watching for the signs that a volcano might be preparing to contribute its cooling influence to the atmosphere. Another remarkable satellite in our volcanic monitoring family is AURA, which carries an instrument specifically designed to track atmospheric chemistry. The Ozone Monitoring Instrument, or OMI, can detect sulfur dioxide in the atmosphere with incredible precision. When a volcano releases SO2, even in relatively small amounts, OMI can spot it from space and track its movement through the atmosphere. This has revolutionized our understanding of how volcanic emissions contribute to global cooling, allowing scientists to measure the process as it happens, rather than trying to reconstruct it after the fact. The data from these satellites tells a story that would have seemed like science fiction just a few decades ago. We can now watch, in real time, as a volcanic eruption injects cooling agents into the atmosphere. We can see how these materials spread and mix with existing atmospheric components. We can track their journey around the globe and measure their impact on global temperatures with a precision that would have amazed early volcanologists. One of the most fascinating discoveries made possible by satellite monitoring is the realization that volcanoes don't just cool the planet during major eruptions. Even when they're quiet, many volcanoes continuously emit small amounts of sulfur dioxide and other gases that contribute to atmospheric cooling. These quiet emissions, invisible to the naked eye, add up over time to create a significant cooling effect. It's like discovering that the Earth has been slowly and steadily applying its own cooling system, operating so quietly that we never noticed it until we had the right tools to look. The Sentinel satellites, part of the European Space Agency's Copernicus program, have added another layer to our understanding of volcanic cooling. These satellites use radar technology to measure tiny changes in the Earth's surface, detecting the subtle swelling and deflation of volcanic ground that indicates magma movement below. When combined with thermal and chemical monitoring, this creates a three-dimensional picture of volcanic activity that helps scientists understand not just when an eruption might occur, but what kind of cooling impact it might have on global climate. The peaceful revolution in volcanic monitoring extends beyond just watching individual volcanoes. Satellites can now provide a global perspective on volcanic activity, allowing scientists to see patterns and connections that were invisible when monitoring was limited to ground-based observations. They have discovered that volcanic cooling effects can interact with each other across vast distances, creating complex patterns of atmospheric chemistry that influence weather and climate on a planetary scale. Perhaps most remarkably, satellite data has revealed that the timing of volcanic eruptions can significantly influence their cooling effects. An eruption that occurs during certain seasons or atmospheric conditions can have a much greater cooling impact than one that occurs at a different time. This discovery has helped scientists understand why some volcanic eruptions seem to cause dramatic global cooling, while others, despite being equally powerful, have more modest effects. The integration of multiple satellite systems has created what scientists call a volcanic monitoring constellation, a network of eyes in the sky that work together to provide comprehensive, real-time information about volcanic activity around the globe. This constellation operates with the quiet efficiency of a well-orchestrated symphony, each instrument contributing its unique voice to create a complete picture of how volcanoes influence our planet's climate. While satellites provide the grand view from space, there's something equally beautiful happening much closer to home. Scattered across volcanic regions around the world, a network of ground-based monitoring stations works quietly and persistently, like patient gardeners tending to the Earth's most dramatic landscapes. These stations, equipped with sensitive instruments, provide what scientists call ground truth, the detailed, intimate knowledge of what's happening right at the source of volcanic activity. Picture a small, weatherproof building perched on the slopes of an active volcano, its solar panels glinting in the morning sun. Inside, sophisticated instruments hum quietly as they record every tremor, every change in gas emissions, every subtle shift in the mountain's behavior. These stations are often located in remote, beautiful places where the only sounds are the wind through volcanic rocks and the occasional rumble from deep within the earth. Yet despite their isolation, they're connected to the global scientific community through satellite links, constantly sharing their observations with researchers around the world. The story of ground-based volcanic monitoring is one of gradual evolution, from simple observations to sophisticated networks of automated instruments. In the early days, monitoring a volcano meant having brave scientists climb its slopes with basic tools, taking measurements by hand and recording observations in field notebooks. Today, that same work is done by networks of instruments that never sleep, never get tired, and never miss a detail, no matter how subtle. One of the most important tools in this ground-based arsenal is the seismometer, an instrument so sensitive it can detect vibrations smaller than the width of an atom. When placed near a volcano, seismometers listen to the Earth's underground conversations, the subtle movements of magma, the cracking of rocks under pressure, the gentle breathing of volcanic systems as they prepare for activity. These instruments have revealed that volcanoes are never truly quiet. They're always whispering, always moving, always preparing for their next contribution to the planet's cooling systems. The gentle precision of modern seismometers allows scientists to distinguish between different types of underground activity. Some earthquake signals indicate the movement of magma toward the surface, suggesting that an eruption and its associated cooling effects might be approaching. Other signals suggest the collapse of underground caverns or the settling of volcanic material. Each type of signal tells a different part of the story of how volcanoes prepare to release their cooling agents into the atmosphere. Gas monitoring stations add another layer of understanding to the ground truth network. These instruments, often tucked into volcanic fumaroles or positioned downwind from active vents, continuously sample the air for volcanic gases. They can detect changes in sulfur dioxide concentrations that might indicate increasing volcanic activity, providing early warning that cooling agents might soon be released into the atmosphere. The beauty of this system is its sensitivity. These instruments can detect changes in gas emissions long before any visible signs of volcanic unrest appear. One of the most fascinating aspects of ground-based monitoring is how it reveals the personality of individual volcanoes. Each volcanic system has its own unique patterns of behavior, its own way of preparing for eruptions, its own signature in the seismic and gas data. Scientists who work with these monitoring networks often speak of their volcanoes with the affection of old friends, recognizing subtle changes in behavior that might be invisible to outsiders, but are as clear as facial expressions to those who know how to read them. The Yellowstone Volcano Observatory provides a beautiful example of how ground-based monitoring networks operate. Scattered throughout Yellowstone National Park, dozens of seismometers, gas sensors, and thermal monitors work together to keep track of one of the world's largest volcanic systems. The data from these instruments is transmitted in real time to scientists who can track every subtle change in the system's behavior. When thermal features change temperature, when gas emissions shift composition, when the ground rises or falls by even tiny amounts, the monitoring network detects and records these changes. What makes this network particularly fascinating is how it reveals the quiet, continuous ways that Yellowstone influences global climate. Even without major eruptions, the volcanic system releases significant amounts of carbon dioxide and other gases that contribute to atmospheric chemistry. The monitoring network has shown that these emissions vary with seasons, with underground magma movements, and with changes in the regional water table. It's like discovering that the Earth has a complex respiratory system, with volcanoes serving as some of its most important breathing mechanisms. Similar networks operate around active volcanoes worldwide, each one adapted to the unique characteristics of its local volcanic system. The Hawaiian Volcano Observatory, one of the oldest continuously operating volcano observatories in the world, has been collecting ground truth data since 1912. Over more than a century of observations, this network has revealed how Hawaiian volcanoes contribute to atmospheric cooling through continuous, gentle emissions of sulfur dioxide and other gases. The data from Hawaiian monitoring stations has shown that volcanic cooling effects don't always require dramatic explosions. The steady, persistent emissions from Hawaiian volcanoes create a continuous input of cooling agents into the atmosphere, contributing to regional and sometimes global climate patterns. This discovery has helped scientists understand that the cooling effects of volcanoes are not just about major eruptions, they're also about the quiet, persistent contributions that volcanoes make to atmospheric chemistry every single day. Modern ground-based monitoring networks also include instruments that measure ground deformation with incredible precision. These instruments, which use GPS technology and sensitive tilt meters, can detect when a volcano's surface rises or falls by amounts measured in millimeters. Such tiny changes often indicate the movement of magma underground, providing early warning that an eruption and its associated cooling effects might be approaching. The integration of different types of ground-based instruments creates a comprehensive picture of volcanic behavior that would be impossible to achieve with any single monitoring technique. When seismic activity increases, gas emissions change, and ground deformation accelerates, scientists can combine these different types of data to understand not just that a volcano is becoming more active, but how that activity might influence global climate. Perhaps most importantly, ground-based monitoring networks provide the detailed, continuous data needed to understand how volcanic cooling effects vary over time. By tracking gas emissions, thermal output, and seismic activity over years and decades, scientists can identify patterns and cycles that help predict when and how volcanoes will contribute to global cooling. This long-term perspective has revealed that volcanic cooling is not random or unpredictable. It follows patterns that can be understood and, to some extent, anticipated. The quiet dedication of these ground-based monitoring networks represents one of humanity's most successful collaborations with the natural world. By listening carefully to what volcanoes are telling us, we've learned to understand their language, to recognize their moods, and to appreciate their crucial role in maintaining Earth's climate balance. These instruments, scattered across volcanic landscapes around the world, serve as translators between the Earth's ancient volcanic systems and our modern understanding of global climate. In the peaceful complexity of Earth's climate system, volcanoes play a role that is both ancient and utterly modern, both dramatic and subtle. Understanding how volcanic cooling effects integrate with the larger climate system requires us to think like detectives, piecing together clues from atmospheric chemistry, ocean temperatures, weather patterns, and the delicate dance of energy that flows between Earth and space. It's a story that connects the deepest parts of our planet with the highest reaches of the atmosphere, revealing connections that are as beautiful as they are scientifically profound. Imagine the Earth's climate system as a vast interconnected web, with every component affecting every other component in ways that can be both immediate and delayed, both obvious and surprisingly subtle. Volcanoes represent one of the most powerful natural forces within this web, capable of sending ripples of change that spread throughout the entire system. When a volcano injects cooling agents into the atmosphere, those effects don't just stay local, they become part of a global conversation between different parts of the climate system. The relationship between volcanic cooling and climate begins in the stratosphere, that quiet layer of atmosphere that sits about 10 to 15 miles above our heads. When volcanic eruptions are powerful enough to reach this high altitude, they deposit sulfur dioxide and other compounds in a region where atmospheric mixing happens very slowly. Unlike the lower atmosphere, where weather systems quickly stir and redistribute atmospheric components, the stratosphere is remarkably stable and calm. Materials injected into this layer can remain there for months or even years, gradually spreading around the entire globe. This slow, persistent presence of volcanic materials in the stratosphere creates what scientists call a radiative forcing, a gentle but persistent change in how much solar energy reaches Earth's surface. The sulfuric acid droplets formed from volcanic sulfur dioxide act like tiny mirrors, reflecting a small percentage of incoming sunlight back to space. This reflection might seem minimal, but when it occurs over the entire planet for months or years, the cumulative cooling effect can be substantial. The beauty of studying these climate connections lies in discovering how different parts of the system respond to volcanic cooling. When volcanic aerosols reduce the amount of sunlight reaching Earth's surface, the effects ripple through the entire climate system in ways that can be both predictable and surprising. Ocean temperatures respond slowly but persistently to changes in solar input. Atmospheric circulation patterns can shift as different regions experience different amounts of cooling. Even the behavior of monsoons and seasonal weather patterns can be influenced by the gentle cooling effects of volcanic aerosols. One of the most fascinating aspects of the volcanic climate connection is how it varies depending on where and when eruptions occur. A volcanic eruption in the tropics can have global effects because the atmospheric circulation patterns in tropical regions help spread volcanic materials around the entire planet. An eruption at higher latitudes might have more regional effects, influencing climate patterns in specific hemispheres rather than globally. The timing of eruptions also matters. Eruptions that occur during certain seasons can have different climate impacts than those that occur at other times of the year. The Mount Pinatubo eruption of 1991 provides a perfect case study in how volcanic cooling integrates with global climate systems. The eruption occurred in the Philippines, near the equator, which meant that the massive amounts of sulfur dioxide injected into the stratosphere were quickly distributed around the globe by tropical atmospheric circulation patterns. Within months, the volcanic aerosols had spread to both hemispheres, creating a global cooling effect that persisted for several years. But the effects of Pinatubo weren't just about global temperature changes. The cooling influenced weather patterns around the world in subtle but important ways. Some regions experienced cooler summers, others saw changes in precipitation patterns, and the behavior of phenomena like El Niño and La Niña were affected by the altered atmospheric conditions. It was like watching a single volcanic event send gentle waves of change throughout the entire global climate system. Modern climate models have become sophisticated enough to simulate these complex interactions between volcanic cooling and global climate. These models, running on powerful computers, can track how volcanic aerosols spread through the atmosphere, how they interact with existing atmospheric components, and how they influence temperature and weather patterns around the world. The models have revealed that volcanic cooling effects are not uniform. Some regions of the planet experience more cooling than others, and these regional differences can influence global atmospheric circulation patterns. One of the most surprising discoveries from climate modeling studies is how volcanic cooling can interact with human-caused climate change. In some cases, volcanic cooling can temporarily offset some of the warming effects of greenhouse gas emissions. This doesn't mean that volcanoes provide a solution to climate change. The cooling effects are temporary, while greenhouse gas effects are persistent and long-lasting. But it does mean that understanding volcanic cooling is crucial for accurately predicting future climate changes. The ocean's response to volcanic cooling provides another layer of complexity to the climate connection. Oceans have enormous thermal mass, which means they heat up and cool down much more slowly than the atmosphere. When volcanic aerosols reduce the amount of sunlight reaching the ocean's surface, the cooling effect can persist in ocean temperatures long after the volcanic aerosols have settled out of the atmosphere. This creates a kind of climate memory, where the effects of volcanic eruptions can influence ocean temperatures and climate patterns for years or even decades after the original eruption. Recent research has also revealed how volcanic cooling can influence the behavior of ice sheets and glaciers. When volcanic aerosols reduce global temperatures, they can affect the rate of ice melting and the behavior of seasonal snow cover. These effects can influence sea level changes and regional climate patterns in ways that extend far beyond the immediate cooling effects of the volcanic aerosols themselves. Perhaps most intriguingly, scientists have discovered that the climate effects of volcanic cooling can influence the behavior of volcanoes themselves. Changes in global temperature and precipitation patterns can affect the stability of volcanic systems, potentially influencing when and how future eruptions occur. This creates a complex feedback loop where volcanic cooling effects can influence the likelihood of future volcanic cooling events. The study of volcanic climate connections has also revealed the importance of considering multiple volcanoes acting together. While individual volcanic eruptions can have significant climate effects, the cumulative impact of many smaller eruptions occurring over time can also be substantial. This has led scientists to develop new ways of thinking about volcanic cooling as a continuous, varying process, rather than just the effects of individual dramatic eruptions. Understanding these climate connections has practical implications for society as well. By better understanding how volcanic cooling affects regional climate patterns, scientists can improve predictions of how volcanic eruptions might influence agriculture, water resources, and weather-dependent activities. This knowledge helps communities prepare for and adapt to the climate effects of volcanic activity. The peaceful complexity of the volcanic climate connection reminds us that Earth's climate system is beautifully interconnected, with natural processes like volcanic cooling playing crucial roles in maintaining the delicate balance that makes our planet habitable. As we continue to study these connections, we gain not just scientific understanding, but a deeper appreciation for the elegant ways that different parts of our planet work together to create the stable climate conditions that have allowed life to flourish. In the quiet corners of research institutions around the world, scientists are engaged in one of the most challenging and important tasks of our time, trying to predict how volcanic cooling will influence Earth's climate in the years and decades to come. It's a task that requires equal parts scientific rigor and creative thinking, combining sophisticated computer models with careful observations of current volcanic activity. The goal is not just to understand what volcanoes have done in the past, but to anticipate how they might continue to influence our planet's climate future. The art of predicting volcanic cooling effects begins with understanding that volcanoes, despite their dramatic and sometimes unpredictable behavior, follow certain patterns that can be studied and, to some extent, anticipated. Just as meteorologists can predict weather patterns by understanding atmospheric dynamics, volcanologists are learning to predict volcanic behavior by understanding the deeper processes that drive volcanic activity. This doesn't mean that scientists can predict exactly when and where eruptions will occur, but they can identify patterns and probabilities that help anticipate future cooling effects. One of the most powerful tools in this predictive effort is the development of increasingly sophisticated computer models that simulate both volcanic processes and their climate effects. These models, running on some of the world's most powerful computers, can simulate how different types of volcanic eruptions might influence global climate under various scenarios. They can explore questions like, what would happen to global temperatures if a major eruption occurred during a particularly warm period? How might climate change influence the way volcanic cooling effects spread through the atmosphere? The beauty of these predictive models lies in their ability to explore what-if scenarios that would be impossible to study through direct observation. Scientists can simulate eruptions of different magnitudes, occurring in different locations under different atmospheric conditions, and see how each scenario might play out in terms of global cooling effects. This helps researchers understand not just what volcanic cooling looks like on average, but how it might vary under different circumstances. Recent advances in volcanic monitoring technology have also improved our ability to predict future cooling effects. The global network of ground-based monitoring stations and satellite observations provides real-time information about volcanic activity around the world. By carefully tracking changes in volcanic behavior, increases in seismic activity, changes in gas emissions, ground deformation, scientists can often identify volcanoes that might be approaching periods of increased activity. This predictive capability doesn't just help scientists understand volcanic cooling, it also helps societies prepare for the potential effects of volcanic activity. When monitoring data suggests that a major eruption might be approaching, communities can prepare for potential climate effects like cooler temperatures, changes in precipitation patterns, or altered growing seasons for agriculture. This preparation can help reduce the impacts of volcanic cooling on human activities and natural systems. One of the most intriguing aspects of predicting volcanic cooling is understanding how it might interact with human-caused climate change. As greenhouse gas concentrations continue to rise in the atmosphere, the background conditions under which volcanic cooling occurs are changing. This means that future volcanic eruptions might have different climate effects than similar eruptions that occurred in the past. Scientists are working to understand these interactions and incorporate them into their predictive models. The challenge of predicting volcanic cooling is complicated by the fact that volcanoes operate on multiple timescales simultaneously. Some aspects of volcanic behavior change over days or weeks, others over years or decades, and still others over centuries or millennia. Understanding how these different timescales interact is crucial for making accurate predictions about future cooling effects. It requires scientists to think both about immediate volcanic hazards and about longer-term patterns of volcanic activity that might influence climate over decades or centuries. Recent research has revealed that the frequency and magnitude of volcanic eruptions might be influenced by climate change itself. As global temperatures rise and ice sheets melt, the changing weight distribution on Earth's surface might influence volcanic activity in some regions. This creates a complex feedback system where climate change influences volcanic activity, which in turn influences climate through cooling effects. Understanding these feedbacks is crucial for making accurate predictions about future climate conditions. Scientists are also working to improve predictions by studying the geological record of past volcanic activity. By examining volcanic deposits, ice core records, and other evidence of past eruptions, researchers can identify patterns in volcanic activity that span thousands or even millions of years. These long-term patterns provide context for understanding current volcanic activity and help scientists assess the likelihood of different types of future eruptions. The development of machine learning and artificial intelligence techniques is opening new possibilities for predicting volcanic cooling effects. These computational approaches can identify subtle patterns in monitoring data that might be invisible to human observers, potentially providing earlier warning of impending volcanic activity. They can also help scientists process the enormous amounts of data generated by global monitoring networks, identifying trends and anomalies that might indicate changing volcanic behavior. One particularly promising area of research involves using ensemble forecasting techniques, similar to those used in weather prediction, to understand the range of possible volcanic cooling effects. Instead of trying to make a single precise prediction, scientists can run multiple simulations with slightly different starting conditions to explore the range of possible outcomes. This approach acknowledges the inherent uncertainty in predicting complex natural systems, while still providing useful information about likely future conditions. The international scientific community has also developed collaborative frameworks for sharing volcanic monitoring data and coordinating research efforts. The Global Volcanism Program, operated by the Smithsonian Institution, maintains comprehensive databases of volcanic activity around the world. These databases help scientists identify global patterns in volcanic behavior and improve their understanding of how volcanic cooling effects might evolve in the future. As our predictive capabilities improve, scientists are also working to communicate their findings more effectively to policymakers and the public. Understanding how volcanic cooling might influence future climate is important not just for scientific research, but for making informed decisions about climate adaptation and mitigation strategies. This requires translating complex scientific predictions into clear, actionable information that can guide decision-making. The peaceful pursuit of predicting volcanic cooling represents one of humanity's most ambitious scientific endeavours, trying to understand and anticipate the behaviour of one of Earth's most powerful natural forces. While perfect prediction may be impossible, the steady improvement in our understanding and forecasting capabilities offers hope that we can better prepare for and adapt to the ways that volcanoes will continue to influence our planet's climate. In this ongoing effort to peer into the future, scientists are not just advancing our knowledge of volcanic processes, but helping humanity develop a more nuanced and sophisticated relationship with the natural forces that shape our world. As we stand at the threshold of a new era in volcanic science, the technologies that help us understand how volcanoes cool the planet are evolving at an unprecedented pace. Picture, if you will, a network of sensors so sensitive they can detect the slightest tremor deep within the Earth, so sophisticated they can taste the chemical signature of gases escaping from volcanic vents thousands of miles away. This is not science fiction. This is the reality of modern volcanic monitoring, and it's painting an increasingly detailed picture of how our planet's fiery mountains continue their ancient work of climate regulation. The satellites that orbit our blue marble today carry instruments that would have seemed magical to the scientists who first theorized about volcanic cooling effects. These orbital sentinels can measure the precise temperature of volcanic lakes, track the movement of sulfur dioxide plumes across entire continents, and even detect the subtle swelling of volcanic slopes that might indicate magma movement far below. It's like having a global nervous system that's constantly feeling the pulse of every active volcano on Earth, understanding their moods and predicting their behaviour with growing accuracy. Consider the remarkable story of the Advanced Very High Resolution Radiometer, or AVHR, a satellite instrument that has been quietly revolutionising our understanding of volcanic climate effects for decades. This technological marvel can detect volcanic ash clouds within hours of an eruption, tracking their movement across the globe with precision that would have astounded early volcanologists. But more importantly for our story of planetary cooling, it can measure the exact concentration of sulfur dioxide in these plumes, helping scientists calculate with increasing accuracy just how much cooling effect each eruption will have on global temperatures. The beauty of these modern monitoring systems lies not just in their individual capabilities, but in how they work together like instruments in a vast planetary orchestra. Ground-based seismometers feel the Earth's trembling, gas sensors taste the chemical breath of awakening volcanoes, thermal cameras watch for the infrared signatures of rising magma, and satellite instruments observe from space, all feeding their data into sophisticated computer models that help us understand the complex relationship between volcanic activity and climate. These models are themselves marvels of human ingenuity, incorporating everything we've learned about how volcanoes cool the planet into mathematical frameworks that can predict the climate effects of future eruptions. They account for the season of the eruption, the latitude of the volcano, the chemical composition of the magma, the height of the eruption column, and countless other factors that influence whether a particular volcanic event will contribute to global cooling or have minimal climate impact. But perhaps the most exciting development in volcanic monitoring is the emergence of machine learning and artificial intelligence as tools for understanding these complex systems. Imagine computer programs that can analyze thousands of years of volcanic and climate data, identifying patterns that human scientists might miss, predicting the likelihood of major cooling events, and helping us prepare for the climate impacts of future eruptions. These digital minds are learning to read the subtle signs that precede major volcanic events, potentially giving us weeks or even months of advance warning when a volcano is preparing to significantly impact global climate. The integration of these technologies is creating what scientists call volcanic hazard early warning systems that extend beyond just protecting human populations from immediate dangers. These systems are beginning to incorporate climate impact assessments, helping us understand not just when a volcano might erupt, but what its eruption might mean for global temperatures, weather patterns, and climate stability. It's a level of understanding that would have seemed impossible just a few decades ago, and it's growing more sophisticated with each passing year. Real-time volcanic monitoring networks now span the globe, with data from remote volcanic regions transmitted instantly to research centres around the world. Scientists can watch volcanic gas emissions change in real time, observe the thermal signatures of volcanic activity as they develop, and track the atmospheric dispersion of volcanic aerosols with precision that allows for increasingly accurate climate impact predictions. This global network creates a comprehensive picture of volcanic activity and its cooling effects that has never before been possible in human history. The implications of this technological revolution extend far beyond academic curiosity. As we face the challenges of anthropogenic climate change, understanding the natural cooling mechanisms provided by volcanic activity becomes increasingly important for climate policy and adaptation planning. These monitoring systems help us understand how volcanic cooling might interact with human-caused warming, providing crucial data for climate models that inform policy decisions around the world. The relationship between volcanoes and climate change is far more complex and fascinating than most people realize. As our planet warms due to human activities, the behavior of volcanic systems themselves may be changing in ways that could affect their ability to cool the planet. It's a story of feedback loops and interconnected systems that reveals just how delicately balanced our planet's climate system truly is. Consider the melting of glacial ice, one of the most visible effects of global warming. When massive ice sheets retreat from volcanic regions, they remove enormous weight from the Earth's crust in a process called isostatic rebound. This gradual lifting of the land can change the stress patterns around volcanic systems, potentially affecting the frequency and intensity of eruptions. Some scientists theorize that this could lead to increased volcanic activity in certain regions, which could, in turn, enhance the natural cooling effects that help moderate global temperatures. The story becomes even more intriguing when we consider how changing precipitation patterns might affect volcanic systems. In many volcanic regions, groundwater plays a crucial role in determining eruption style and intensity. As climate change alters rainfall patterns and snowpack accumulation, the hydrology around volcanic systems changes as well. This can affect everything from the explosiveness of eruptions to the types of gases released, potentially altering the climate impact of volcanic activity. There's also the fascinating question of how ocean temperature changes might affect underwater volcanic activity. The vast majority of Earth's volcanoes are actually beneath the ocean surface, and these submarine volcanoes play important roles in ocean circulation and chemistry. As ocean temperatures rise and circulation patterns change, the behavior of these underwater volcanic systems may shift as well. While submarine eruptions don't typically inject materials high enough into the atmosphere to create significant cooling effects, they do influence ocean chemistry and circulation patterns that affect global climate in subtle but important ways. Perhaps most intriguingly, some researchers are investigating whether the timing of volcanic eruptions might be influenced by climate patterns. There's emerging evidence that some volcanic systems may be sensitive to seasonal variations, atmospheric pressure changes, and even long-term climate cycles. If this proves to be true, it could mean that volcanic cooling effects are not randomly distributed through time, but may have subtle relationships with natural climate variability. The interaction between volcanic cooling and human-caused warming creates a complex dance of competing forces. During periods of high volcanic activity, natural cooling effects can temporarily mask some of the warming caused by greenhouse gas emissions. This has actually happened several times in recent decades, when major eruptions like Mount Pinatubo created temporary pauses in global temperature rise. However, these cooling effects are temporary, lasting only a few years, while greenhouse gas effects persist for decades or centuries. This temporal mismatch highlights one of the most important aspects of volcanic cooling in the context of climate change. While volcanoes can provide temporary relief from warming, they cannot solve the long-term challenge of anthropogenic climate change. The cooling effects of even the largest eruptions fade within a few years, while the warming effects of greenhouse gases accumulate over much longer timescales. It's like trying to cool a steadily heating room by occasionally opening a window. The brief relief is welcome, but it doesn't address the underlying heat source. Yet this doesn't diminish the importance of understanding volcanic cooling effects. As climate scientists work to predict future temperature trends and develop strategies for climate adaptation, accurate accounting of natural climate variability, including volcanic cooling, becomes crucial. Volcanic eruptions will continue to provide periodic cooling effects that must be factored into climate projections and policy planning. Some researchers are even investigating whether lessons learned from natural volcanic cooling could inform human climate intervention strategies. The idea of solar radiation management, deliberately introducing particles into the stratosphere to mimic the cooling effects of volcanic eruptions, draws directly from our understanding of how volcanoes cool the planet. While such approaches remain highly controversial and fraught with risks, they represent one way that our knowledge of volcanic climate effects might inform responses to climate change. The study of past volcanic cooling events also provides valuable insights into how the climate system responds to rapid changes in radiative forcing. By understanding how the Earth's climate recovered from major volcanic cooling events in the past, scientists can better understand the resilience and sensitivity of the climate system, information that is crucial for predicting how the climate might respond to various future scenarios. Beneath the surface of our understanding of how volcanoes cool the planet lies a vast network of interconnected effects that scientists are only beginning to fully appreciate. These hidden connections reveal that volcanic cooling is not simply a matter of particles blocking sunlight, but part of a complex web of interactions that touch every aspect of Earth's climate system. Take, for instance, the way volcanic eruptions can influence the behavior of monsoon systems that provide life-giving rains to billions of people. When a major volcanic eruption cools global temperatures, it doesn't do so uniformly. The cooling tends to be stronger over land than over oceans, and this temperature difference drives the monsoon systems that bring seasonal rains to much of Asia, Africa, and the Americas. By altering these temperature gradients, volcanic cooling can strengthen or weaken monsoons, affecting rainfall patterns across vast regions of the planet. The story becomes even more intricate when we consider how volcanic aerosols interact with clouds. These tiny particles don't just block sunlight directly, they also serve as nuclei around which cloud droplets can form. This process, called cloud condensation nucleation, can actually increase the number of cloud droplets while making each individual droplet smaller. The result is clouds that are brighter and longer lasting, creating an additional cooling effect beyond the direct shading provided by the volcanic particles themselves. This cloud interaction effect can persist long after the original volcanic particles have settled out of the atmosphere. The changed cloud properties can alter precipitation patterns, which in turn affect vegetation growth, soil moisture, and even the reflectivity of the land surface. It's a cascade of effects that can extend the climate impact of a volcanic eruption far beyond the few years that the volcanic particles remain in the atmosphere. Ocean circulation represents another fascinating dimension of volcanic climate effects. When volcanic cooling changes temperature patterns across the globe, it affects the density differences that drive ocean currents. These currents are like vast conveyor belts that transport heat around the planet, and even small changes in their strength or path can have significant climate consequences. Some research suggests that major volcanic eruptions can affect ocean circulation patterns for decades, creating long-term climate effects that persist long after the volcanic particles have disappeared from the atmosphere. The interaction between volcanic cooling and atmospheric circulation patterns reveals yet another layer of complexity. Phenomena like the North Atlantic Oscillation, the El Niño Southern Oscillation, and the Arctic Oscillation are all potentially influenced by the temperature changes caused by major volcanic eruptions. These circulation patterns affect weather and climate across entire continents, meaning that a volcanic eruption in one part of the world can influence weather patterns thousands of miles away through these atmospheric teleconnections. Perhaps most remarkably, scientists are discovering that volcanic eruptions can even influence the behavior of other volcanic systems. The stress changes caused by large eruptions can propagate through the Earth's crust, potentially triggering increased activity in volcanic systems hundreds or even thousands of miles away. This means that the cooling effects of one eruption might be followed by cooling effects from secondary eruptions, creating clustering effects that enhance the overall climate impact. The biological dimension of volcanic cooling effects adds yet another layer to this complex story. When volcanic particles reduce the amount of sunlight reaching Earth's surface, they affect photosynthesis in plants and phytoplankton. This can alter the growth rates of forests, grasslands, and marine ecosystems, which in turn affects the carbon cycle. Changes in vegetation can influence how much carbon dioxide is absorbed from the atmosphere, creating feedback effects that can either amplify or moderate the climate impacts of volcanic cooling. Seasonal timing plays a crucial role in determining the ultimate climate impact of volcanic eruptions. An eruption that occurs in spring might have very different effects than one occurring in autumn, because the seasonal cycle of solar radiation interacts with the light-blocking effects of volcanic particles. Summer eruptions in the northern hemisphere, when solar radiation is at its peak, tend to have stronger cooling effects than winter eruptions, when there's less sunlight to block in the first place. The altitude at which volcanic particles are injected into the atmosphere creates another dimension of variability in cooling effects. Particles injected into the lower atmosphere tend to be washed out by the precipitation within weeks or months, while those that reach the stratosphere can persist for years. But the height within the stratosphere also matters. Particles injected higher up may spread more effectively around the globe, while those at lower stratospheric altitudes might remain more localized in their effects. Even the chemical composition of volcanic emissions affects their cooling potential in complex ways. Different types of sulfur compounds have different efficiencies for forming aerosol particles, and the presence of other chemicals can either enhance or inhibit aerosol formation. The acidity of volcanic particles affects their interactions with atmospheric chemistry, potentially influencing ozone concentrations and other atmospheric processes that affect climate. To truly understand how volcanoes cool the planet, we must journey back through Earth's deep history, where the geological record preserves evidence of volcanic cooling events that dwarf anything experienced in recorded human history. These ancient episodes offer profound insights into the power of volcanic climate effects and the resilience of Earth's climate system. The geological record speaks of super eruptions, volcanic events so massive they're almost beyond human comprehension. The Toba eruption, which occurred about 74,000 years ago in what is now Indonesia, ejected over 2,800 cubic kilometers of material into the atmosphere. To put this in perspective, this single eruption released more material than 1,000 Mount St. Helens eruptions combined. The climate effects were correspondingly dramatic, with some estimates suggesting global temperatures dropped by as much as 3 to 5 degrees Celsius for several years following the eruption. Evidence for this ancient cooling comes from ice cores, lake sediments, and other geological archives that preserve the chemical signatures of this successive volcanic event. The story they tell is one of a planet thrown into a volcanic winter so severe that it may have pushed human populations to the brink of extinction. Archaeological evidence suggests that human populations declined dramatically during this period, possibly reduced to just a few thousand individuals worldwide. It's a sobering reminder of just how powerful volcanic cooling effects can be when they occur on a massive scale. But the Toba eruption was far from unique in Earth's history. The geological record preserves evidence of dozens of super eruptions, each one creating climate effects that reshaped ecosystems and influenced the course of evolution. The Yellowstone region, now known for its geysers and hot springs, has produced at least 3 super eruptions over the past 2 million years. Each one would have created global cooling effects lasting for years or decades, fundamentally altering climate patterns across the entire planet. These ancient cooling events offer valuable insights into how the Earth's climate system responds to and recovers from extreme volcanic perturbations. The geological record shows that even the most severe volcanic cooling events are temporary. The climate system eventually returns to its pre-eruption state as volcanic particles settle out of the atmosphere and natural processes restore radiative balance. This resilience of the climate system is itself a remarkable feature of our planet. Perhaps even more fascinating are the records of extended periods of volcanic activity, when multiple eruptions occurred in relatively short geological timespans. The Deccan Traps in India, formed by massive volcanic activity about 6 million years ago, created one of the largest volcanic provinces on Earth. The cooling effects from this extended period of volcanism may have contributed to the mass extinction event that ended the age of dinosaurs, though the exact role of volcanic cooling versus other factors remains a subject of ongoing scientific debate. The study of these ancient volcanic cooling events has also revealed surprising insights about the relationship between volcanism and ice ages. Some periods of increased volcanic activity appear to coincide with the initiation or intensification of glacial periods, suggesting that volcanic cooling might sometimes trigger longer-term climate changes. The feedback mechanisms involved are complex, involving interactions between volcanic cooling, ice sheet formation, ocean circulation changes, and atmospheric composition shifts that can sustain altered climate states for thousands of years. Marine sediment cores provide another window into ancient volcanic cooling events, preserving records of how ocean temperatures and circulation patterns responded to major eruptions. These records show that volcanic cooling effects can propagate through the ocean system, affecting marine ecosystems and biogeochemical cycles in ways that persist long after atmospheric effects have faded. The deep ocean, with its slow circulation and long memory, can preserve the signatures of volcanic cooling events for decades or even centuries. Tree ring records extend our understanding of volcanic cooling effects back over several thousand years, providing high-resolution records of how forest ecosystems responded to historical volcanic events. These biological archives show that even moderate volcanic eruptions can cause measurable reductions in tree growth rates across entire continents, effects that sometimes persist for several growing seasons as ecosystems adjust to altered temperature and precipitation patterns. The study of ancient volcanic cooling events has also revealed the importance of timing and context in determining climate impacts. Volcanic eruptions that occurred during naturally cool periods in Earth's history had different effects than those that occurred during warm periods. This context dependence suggests that the cooling effects of future volcanic eruptions will depend not just on the characteristics of the eruptions themselves, but on the background climate state in which they occur. Archaeological evidence provides human-scale perspectives on ancient volcanic cooling events, showing how past civilizations adapted to or were disrupted by major volcanic climate perturbations. The 1815 eruption of Mount Tambora, which caused the year without a summer in 1816, provides a relatively recent example of how volcanic cooling can affect human societies through crop failures, famine, and social disruption. These historical lessons offer insights into how future societies might need to prepare for similar events. As we stand on the threshold of new discoveries about how volcanoes cool the planet, the future of volcanic climate science holds extraordinary promise. Emerging technologies, new theoretical frameworks, and innovative research approaches are opening doors to understanding that would have seemed impossible just a generation ago. The story of volcanic cooling is far from over. In many ways, we're just beginning to appreciate the full complexity and importance of these natural climate regulators. Artificial intelligence and machine learning are revolutionizing our ability to analyze the vast data sets that modern volcanic monitoring systems generate. Imagine computer algorithms that can identify subtle patterns in volcanic gas emissions, seismic signals, and satellite imagery that human scientists might miss. Patterns that could reveal new insights into how volcanic systems behave and how their climate effects develop. These digital tools are learning to recognize the signatures of impending eruptions, predict the likely climate impacts of volcanic activity, and identify previously unknown connections between volcanic events and climate variability. The development of new atmospheric chemistry models is providing unprecedented insights into the complex processes that convert volcanic emissions into climate-affecting aerosols. These models can simulate the intricate chemical reactions that occur in volcanic plumes, predict how particles will evolve as they spread through the atmosphere, and calculate their ultimate climate effects with growing precision. It's like being able to follow individual volcanic particles on their journey through the atmosphere, watching as they transform and interact with other atmospheric components to create the cooling effects we observe. Advances in satellite technology are opening new windows into, volcanic climate effects. Next-generation instruments will be able to measure volcanic emissions with unprecedented precision, track particle dispersal in 3 dimensions, and observe climate effects in real time as they develop. Some proposed satellite missions would create constellations of instruments specifically designed to monitor volcanic climate effects, providing global coverage with temporal resolution that could capture the rapid evolution of volcanic plumes and their atmospheric interactions. The integration of volcanic climate research with Earth system science is revealing new connections between volcanic activity and other components of the climate system. Research programs are now investigating how volcanic cooling interacts with carbon cycle processes, ocean circulation patterns, ecosystem dynamics, and human systems. This holistic approach is showing that volcanic climate effects are embedded within a complex web of Earth system interactions that amplify, modulate, and extend their impacts in ways we're only beginning to understand. Laboratory experiments are providing new insights into the fundamental physics and chemistry of volcanic climate effects. Researchers can now recreate the conditions of volcanic plumes in sophisticated laboratory facilities as studying the formation and evolution of aerosol particles under controlled conditions. These experiments are revealing the detailed mechanisms by which volcanic emissions become climate-affecting particles, providing the fundamental understanding needed to improve our predictive capabilities. The development of paleovolcanic databases is creating comprehensive records of past volcanic activity and its climate effects extending back hundreds of thousands of years. These databases integrate information from ice cores, sediment cores, tree rings, and other geological archives to create detailed chronologies of volcanic cooling events throughout Earth's history. This long-term perspective is essential for understanding the full range of volcanic climate effects and their role in natural climate variability. International collaboration is becoming increasingly important in volcanic climate research, as scientists recognize that understanding these global phenomena requires coordinated efforts across national boundaries. New research networks are sharing data, standardizing measurement techniques, and coordinating research efforts to create a truly global understanding of volcanic climate effects. These collaborative efforts are essential for addressing questions that span multiple volcanic regions and climate zones. The application of volcanic climate research to climate services is beginning to provide practical benefits for society. Improved understanding of volcanic cooling effects is being incorporated into seasonal climate forecasts, agricultural planning tools, and climate adaptation strategies. This applied research is showing how scientific understanding of volcanic climate effects can be translated into societal benefits, helping communities prepare for and adapt to the climate impacts of future volcanic activity. Emerging research into the potential for volcanic geoengineering is exploring whether lessons learned from natural volcanic cooling could inform technological approaches to climate intervention. While such approaches remain highly speculative and controversial, they represent one way that our growing understanding of volcanic climate effects might contribute to responses to anthropogenic climate change. These studies are providing valuable insights into the potential benefits and risks of deliberately mimicking natural volcanic cooling processes. The future of volcanic climate science also lies in improved integration with climate policy and decision-making processes. As our understanding of volcanic cooling effects becomes more sophisticated, it's being incorporated into climate models used for policy assessment, helping provide more accurate projections of future climate that account for natural volcanic variability. This integration ensures that our growing scientific understanding translates into better informed climate policies and adaptation strategies. As our journey through the fascinating world of volcanic cooling draws toward its conclusion, we find ourselves marveling at the extraordinary balance that characterizes our planet's climate system. The story of how the volcanoes cool the planet is ultimately a story about equilibrium, the delicate dance of forces that has kept Earth's climate within bounds suitable for life for billions of years, even as individual components of the system have varied dramatically over time. Think about the remarkable fact that throughout Earth's long history, despite massive volcanic eruptions, asteroid impacts, continental drift, and evolving atmospheric composition, our planet has maintained temperatures that allow liquid water to exist at the surface. This is not a coincidence or a simple stroke of luck. It's the result of numerous feedback mechanisms, including volcanic climate effects, that work together to maintain planetary habitability even in the face of major perturbations. Volcanic cooling effects represent just one thread in this complex tapestry of climate regulation, but it's a crucial thread that has influenced the course of Earth's climate history in profound ways. Every major volcanic eruption has contributed to this long-term story of climate stability, providing temporary cooling that has helped moderate extreme warming events, influence the timing of ice ages, and shape the evolution of life on Earth. The beauty of volcanic cooling lies not just in its immediate effects, but in how it demonstrates the interconnectedness of Earth's systems. When a volcano erupts, it doesn't just change atmospheric composition, it influences cloud formation, ocean circulation, weather patterns, ecosystem dynamics, and even geological processes through the complex web of cause and effect that characterizes our planet. These interconnections remind us that Earth functions as an integrated system where changes in one component can cascade through the entire network of planetary processes. Modern research is revealing that volcanic cooling effects are far more nuanced and sophisticated than early scientists imagined. Rather than simple cooling events that uniformly affect the entire planet, volcanic eruptions create complex patterns of climate change that vary with geography, season, and atmospheric conditions. Some regions might experience cooling while others experience warming. Some seasons might be more affected than others, and the timing of effects can vary from immediate impacts to delayed responses that unfold over years or decades. This complexity is actually a strength of the Earth's climate system, not a weakness. The varied and nuanced nature of volcanic climate effects means that different regions and ecosystems experience different impacts, reducing the likelihood that any single volcanic event could cause planet-wide catastrophe. The resilience built into Earth's climate system through this geographic and temporal variability has helped life survive even the most dramatic volcanic cooling events in Earth's history. The study of volcanic cooling effects also reveals something profound about the relationship between geological and biological processes on Earth. Volcanic activity affects climate, which affects ecosystem, which affect atmospheric composition through photosynthesis and respiration, which affects climate in a continuous cycle of interaction. Life and geology are not separate phenomena on Earth. They're intimately connected participants in the planetary system that maintains habitability. As we face the challenges of anthropogenic climate change, understanding natural climate regulation mechanisms like volcanic cooling becomes increasingly important. These natural processes provide context for understanding how unusual current human-caused climate changes are, benchmarks for evaluating the magnitude of anthropogenic effects, and insights into how the climate system might respond to future changes. Volcanic cooling won't solve human-caused climate change, but understanding it helps us better comprehend the climate system we're affecting. The ongoing evolution of volcanic climate science promises to deepen our appreciation for these natural cooling mechanisms. Each new discovery reveals additional layers of complexity and sophistication in how volcanic eruptions interact with the climate system. Far from being simple, one-dimensional cooling events, Volcanic eruptions emerge from modern research as multifaceted phenomena that influence virtually every aspect of Earth's climate through mechanisms that operate across multiple timescales and geographic scales. Perhaps most remarkably, the story of volcanic cooling demonstrates the power of scientific inquiry to reveal hidden connections and unexpected relationships in the natural world. The fact that explosive events occurring deep within the Earth can influence global climate, affect monsoon patterns on distant continents, alter ocean circulation, and even influence the behavior of ecosystems shows how scientific research can uncover the subtle threads that connect seemingly unrelated phenomena. The future holds the promise of even deeper understanding of these connections. As monitoring technology improves, computer models become more sophisticated, and international collaboration expands, our ability to understand and predict volcanic climate effects will continue to grow. This growing knowledge will enhance our overall understanding of how Earth's climate system functions and how it might respond to future changes, both natural and human-caused. In contemplating the role of volcanic cooling in Earth's climate system, we're reminded of the privilege of living on a planet where such intricate regulatory mechanisms exist. The existence of natural processes that help maintain climate stability over geological timescales is not something we should take for granted. It's a remarkable feature of our planetary home that has made the evolution and persistence of life possible. As we conclude this exploration of how volcanoes cool the planet, we're left with a sense of wonder at the complexity and elegance of natural climate regulation mechanisms. Every volcanic eruption is both a dramatic geological event and a subtle climate adjustment, contributing to the long-term story of how Earth maintains conditions suitable for life. In understanding these processes, we gain not just scientific knowledge, but a deeper appreciation for the remarkable planet we call home and our responsibility to protect the delicate balance that has sustained life for billions of years. The gentle rumbling of distant volcanoes reminds us that these cooling mechanisms continue their ancient work even as you read these words. Somewhere on Earth, volcanic gases are mixing with atmospheric chemistry. Particles are scattering sunlight back to space, and the slow, steady work of natural climate regulation continues. It's a process that has been ongoing for billions of years and will continue long after human civilization has transformed or passed away, a testament to the enduring power of natural processes to maintain planetary habitability through the gentle, persistent influence of volcanic cooling. Thank you for staying with me through this Sisyphal journey into how volcanoes cool the planet. I hope that as you go about your daily life, you'll sometimes pause to appreciate the hidden climate processes happening all around us. The volcanic particles high in the stratosphere scattering sunlight, the complex atmospheric chemistry that converts volcanic gases into cooling aerosols, and the slow circulation patterns that distribute these effects around our beautiful interconnected world. If this gentle exploration of volcanic cooling has sparked your curiosity about our planet's climate system, I encourage you to continue learning about the fascinating processes that maintain Earth's habitability. Every aspect of our climate system, from the smallest atmospheric particle to the largest ocean current, plays a role in the intricate dance that keeps our planet suitable for life. Understanding these processes not only satisfies our natural curiosity, but also helps us make informed decisions about how to protect and preserve the delicate balance that has sustained life on Earth for billions of years. Thank you for joining me in this contemplation of one of nature's most elegant climate regulation mechanisms. May your days be filled with wonder at the hidden processes that make life on our extraordinary planet possible, and may you find peace in knowing that even in times of rapid change, the Earth continues its ancient work of maintaining the delicate balance that sustains us all. Until we meet again in another exploration of our remarkable world, take care and remember to look up at the sky sometimes and appreciate the invisible volcanic particles that may be helping to moderate our planet's temperature at that very moment. Sweet dreams, and thank you for allowing me to share this fascinating story of how volcanoes cool the planet. The Earth's gentle climate regulation mechanisms continue their work while we sleep, maintaining the stable conditions that make our dreams and our lives possible.